Vanakkam Senthil sir, good morning. Vanakkam Sanjeev sir.
Live stream கொஞ்சம் அவர் பார்த்துட்டு இருக்கார் சார், அதனால தான் சார்.
Okay.
Hi, good morning.
Sir. Welcome,
This is Sanjeev Kumar. Good morning. Good morning to all.
Very good morning. Very good morning, sir. Very good morning, sir. Jenistry?
Yes, sir.
Please introduce and start the brief introduction about.
Okay, sir. Today was not like yesterday and never be like tomorrow. So live to the fullest and make the most of every day. Good morning, everyone gathered here. We are so pleased to welcome you all for the third day of IGEN GENDISTRANSCON 2021. We had a grand inaugural function with Himanshu Patel sir. Followed by that, we had eminent speakers yesterday with interesting student presentation, parent presentation, and research meet sessions. And even today, it's going to be very intriguing with our distinguished guests. And we will have a conclave with accomplished speakers, and the most insightful debate will be held on. So participants are asked to be very active and enjoy the session. So to get into the event, I request Mr. Natarajan sir to give the guest profile of today's chief guest.
அனைவருக்கும் வணக்கம். I'm really privileged to read out the profile of Professor Dr. Sanjeev Kumar Padmanabhan. He received PhD degree Electrical Engineering from the University of Bologna, Italy, 2012. He was an associate professor at VIT University from 2012 to 13. In 2013, he joined the National Institute of Technology as a faculty member. In 2014, he was invited as a visiting researcher at Department of Electrical Engineering, Qatar University, Doha, Qatar, funded by Qatar National Research Foundation, Government of Qatar. He continued his research activities with the Dublin Institute of Technology, Dublin, Ireland in 2014. Further, he served as an associate professor with the Department of Electrical and Electronics Engineering, University of Johannesburg, South Africa from 2016 to 18. From March 2018 to February 2021, he has been a faculty member with the Department of Energy Technology, Heidelberg University, Esbjerg, Denmark. Since March 2021, he was working as a professor with CTIF Global Capsule CGC Laboratory, Department of Business Development and Technology, Herning University, Herning, Denmark. S. Padmanabhan has authored over 300 scientific papers and was a recipient of the Best Paper cum Most Excellence Research Paper Award for IET SysCon 13, IET SEET 16, IEEE EECSI 19, IEEE SynCon 19, and first and 5 Best Paper Award for ETAEERE 16, sponsored lecture notes in electrical engineering, Spring Book. He is a fellow of Institution of Engineers, India, Institution of Electronics and Telecommunication Engineers, India, and the Institution of Engineering and Technology, UK. He is an editor, associate editor, editor board of referred journals, in particular the IEEE System journals, IEEE Translation on Industry Application, IEEE Access, IET Power Electronics, IET Electronics Letters, and Wheelie International Transaction on Electrical Energy System. Subject editorial board member, Energy Sources, Energy Journal, IDP, MDPI, and subject editor for IET Renewable Power Generation, IET Generation Transmission and Distribution and Facts Journal. We are eagerly waiting for your dynamic speech, sir. Handed over the session to Dr. Professor Sanjeev Kumar Padmanabhan. Thank you.
Good morning to one and all, and it's a great honor. Thanks to Professor Ramesh for the IGEN, of course, to Professor Senthil Kumar, who has given me an invitation to join this session. I face one problem with the bandwidth, I don't know, but anyway, I will manage, and I like to share my views, which we have been developing in our labs for a long time on these electric vehicles, about what are the futures. We are giving an overview this time. So these works are started in Aalborg University when I was working in the electronics group, and we have been working, I'm closely working with two universities now, with Aalborg University and of course with the Aarhus University in Denmark. So I work for both the universities. So here I like to give you some view on what is the future of electric vehicles, because electric vehicles is the prominent future now for an entire world to overcome the problem of CO2 emission. So in this case, when we look at the electric vehicle as an electrical engineers, we focus more on the first point is on the developing a new modern technologies on motor developments, which is a cheaper cost, battery technology, and storage is very important, because all the vehicles are moving towards completely fossil fuel based electric vehicle systems. So then the challenge is on battery design. Of course, we are looking for other than the batteries, because batteries are very expensive, lithium at present what we are using, and of course the lifetime is not infinite when compared to IC engines. Batteries are much expensive. Batteries are cannot be, of course, at present technology we can't be able to recycle, so the residue is a big challenge. Still, these electric vehicles, which is a part of a system, is dominated by different companies like Nissan, Chevrolet, and Tesla. Of course, there is a indigenous companies from always the indigenous products plays a critical role. In case of Chinese company, BYD plays a critical role because they are the cheapest solution at present available for electric vehicles, but the reliability depends on the price of the requirement of the consumers. So we have different type of electric vehicles. We can have a look. Generally, we say the classification of electric vehicle is given by Electrotechnical Commission, Technical Committee 69, which is organized from the United States. How they give the classification of electric vehicles is based on following classification. We can have IC engine plus battery, or we can have battery plus flywheel, high power applications, or we can have battery plus capacitors, or we can have battery plus fuel cell, which is going to be the future because for the cost optimization and high powertrain applications. And we can have replace these batteries by capacitors or ultra capacitors. Then we can able to optimize the price. So this is the complete classification we have in electric vehicles. Based on these classifications, we have to give a terminology to have a battery based electric vehicle or a hybrid electric vehicle or plug-in electric vehicle, and of course a fuel cell. Fuel cell is going to be the future. Obviously there is no replacement until we find for a high power application where a petrol can or diesel can be replaced absolutely with fuel cell. About battery vehicles, the most important battery vehicles go up to 250 kilometers from 100 kilometers, depends on the road condition, loading, and depends on the vehicle. It can go up to 500 kilometer maximum in top tiers in foreign countries like United States or US, because the road conditions and the facilities are very good in these circumstances. That's why these conditions, it can be helpful for the applications of I face a technical problem here, so just hold on a second. On this Sunday I'm facing a technical problem.
Okay, sir. Okay.
So okay, Said. So these vehicles or can be, we can also think about the possibilities with battery model. So battery model is very simple. We have a battery bank which is controlled by an inverter which converts the DC to AC, and we can propel the motor and the gear train for a differential speed control of electric vehicle. The drawback, this system can be applicable only for a domestic application or a home application, but not for a real transportation systems. It's very complex because we can't have much high power train. So we have to look for other possibilities of electric vehicles. One is the possibility is a hybrid electric vehicle where we still use the IC engines along with electric motor. So we have different mode of operation. That possibility we can able to store the energy in the battery from the electric motor because we have a revolution. So it's like a dynamo. We can able to store the energy from the electric motor pumped to the battery during the starting condition. Of course, during the stop condition, the battery has to be work like a plug-in. So we have to plug in the power supply from the grid or from the home application. We can store the battery. The most important is the running conditions like passing, braking, and cruising. During this condition, both IC engine as well as the battery can power the powertrain parallelly during the passing condition. Braking condition, we apply the brake for the motor. So regenerative braking is available. We can pump the power back to the battery and we can save the energy even during the braking condition. Other possibility during the running cruising condition, the motor is continuous propulsion. So the power generated from induction motor or synchronous motor or any other special purpose motor which is used in the electric vehicle depends on its classification. We can pump the power back to the battery. So these are the possibilities to use available electric vehicles, which is having both IC engine as well as the batteries. The extended version is going to be the plug-in hybrid electric vehicle. So the plug-in hybrid vehicle, the big challenge is to design the battery because the battery capacity should be equivalent to the IC engine capacity, which is a big task, and it consumes a lot of cost. And the battery design is not so easy because lithium battery is presently used in all electric vehicles, so it's very expensive. So these models also available in Chevrolet and Toyota, which is a popular company which produce a hybrid electric vehicle. The future is going to be the fuel cell based electric vehicle along with the battery because the major problem is the generation of these fuel cells because it costs very high, $200 per kilowatt, whereas IC engine is $50 per kilowatt. So the comparison shows very clearly it is very expensive, but still the model is readily available for commercial applications like companies from Toyota and Honda. They manufacture large scale hydrogen vehicles. Of course, in EU states, in Denmark, where I'm from, we use a lot of hydrogen based electric vehicles for, if of course, for domestic or also for the transportation purposes, large scale trucks, etc. Because in order to overcome the problem of CO2 emission, hydrogen generation is another scarcity problem. We are looking at new technologies from the point of hydrogen people who are working, how we can make more optimized hydrogen. And about other possibilities, we can, so I don't want to explain how an hydrogen power generation has been carried out in electric vehicle because it's a general concept as standard applications. But I'm most focused on how we can able to reduce the price of the hydrogen. Either we can use batteries or supercapacitors, which can compensate the price of fuel cell utilization by a factor like 40%. So 40% power will come from the battery and 60% power will come from the fuel cell. In this way, we can able to balance the expense of the electric vehicle by using modern technologies. Of course, battery is very expensive, so we can think about ultra capacitors or supercapacitors. And of course, we have flywheels which can store large energy, which are much efficient than batteries. For example, how hydrogen is being implemented in the first case, usually they adapted in race cars. Finifera H2 is the first model which introduced hydrogen fuel cell, and the capacity is very high. And of course, these models now, the same vehicles which are used for sports applications are converted into commercial vehicles. And recently in United States, about 45% of vehicles are based on plug-in electric vehicles, which uses both fuel cell as well as the battery. So batteries are consuming the power from the grid, from the home application during the night time. Of course, in the future, the plan is to pump the power from the battery to the grid. So each electric vehicle can be a entrepreneur or can able to consume the energy, the benefits from the grid operators. If you look at the statistics, that's most important about how a battery as well as the fuel cell market growing up. And there is a border between battery based electric vehicles and fuel cell based electric vehicles. Always the fuel cell based electric vehicles dominate the system, and there is a combination because it looks depends on the weight, vehicle weight, storage volume, greenhouse gases, and natural gas required. Biomass, of course, now used for the grid application. So they use waste to electricity power generation in modern countries like Denmark and Netherlands, Norway, and Sweden, where they use all these waste material. Of course, all the garbages are turned into electricity. So they use these power for powering the electric vehicles. And in Denmark is the most wind energy system. 45% of the energy is from the wind. But if you look at the wind application towards microgrids, which charges the electric vehicles, we need sufficient battery vehicle. That's why you can see the percentage is less. And of course, the wind and car, always the most important factor ratio goes to very high because wind is an expensive project, and Denmark is focusing more towards wind and to have renewable energy 100% by 2035. So that's why the ratio between the utilization of battery, wind, and fuel cell is very high when we are going for wind power. And about the incremental cost, yes, because we are focusing more on modern electric vehicles with non-conventional fuels, the cost goes very high in the ratio of fuel cells and of course battery. And this is another challenge for all the engineers to look at how to reduce the price. And most important, the fuel cost per kilometer comes down because most of them are batteries, and of course the price little high because of the fuel cells. And about the life cycle cost is reduced when compared to IC engine because we don't want a continuous maintenance of the batteries or fuel cell. They are more reliable than IC engines. So in conclusion, I can say a comparison, we have different types of electric vehicles, battery-based electric vehicles. They use batteries, ultra capacitors as a energy storage system within the vehicle, and there is no emission. They are commercially available, and the drawback is very expensive because of the battery, and still the range is not decided. Charging time are very high because not less than 30 minutes is required to charge the battery. So obviously 6 hours is the maximum time for charging the full capacity. So we need to look for fast charging electric vehicles, and the price is very high. And we are looking at another point is a hybrid electric vehicle. In hybrid electric vehicle, we use IC engine along with electric networks for the storage capacity. So storage capacities are done by ultra capacitors, IC engine, and battery. It's a combination. Obviously, when you have such systems, the major challenge is on energy storage. For example, now all the electric vehicles adapt as control systems based on AI technology to control a mechanical system and an electrical system simultaneously is a big challenge for the engineers to govern optimized control algorithms. And in this case, a big challenge is again between the capacity of battery requirement, because battery requirement should be equivalent to IC engine, which is very, very expensive. And we have some future benefits because it emits very little emission because of the IC engine, but it can be used for long range, very high power application. The structure, even though it's a complex, but benefits to the consumers for long drive applications and a huge propulsion network required for trucks, etc. And they are obviously available commercially. And the future, we are looking at fuel cell based electric vehicles where we have only electric power system. There is no any mechanical power system. And the major fuel is going to be the fuel cell along with the batteries and ultra capacitors or flywheels, etc. for high power applications. And here we will have a very little emission when compared to IC engines because of the hydrogen, but efficiency is very high when compared to IC engines, and price obviously very high. That is a big drawback. And they are also available in commercial market. Problem, how to reduce the price of these hydrogen power generation. What are the new technology which can have high efficiency, because the efficiency of the fuel cell is only 60% when compared to electric circuits, which is about 85%. If you look at an electric vehicle, this is standard model. In the future, we are looking at modern electric vehicles, how it works. So the energy management plays a critical role with AI algorithms. And one side, we have electric networks with propulsion, with power electronics converters. We have a control units for accelerators and brakes. power converter, which controls bidirectional power flow between mechanical parts and electrical parts. So electrical motor is controlled by power electronics converters, whereas the mechanical transmission is controlling the wheels. And most important is the energy storage network. So within the electric vehicle, we can have mechanical energy storage systems as well as electric storage systems. And these all are controlled by AI algorithms with all safety measures. Apart from that, we have auxiliary units, which is very important. Now we are using a lot of batteries. So battery control temperature is a very complex parameters. Otherwise, we'll have explosion. Of course, hydrogen is a very explosive system in the network. So temperature control plays a critical role in auxiliary subsystem unit, which controlled by again by the power electronics converters and electronics units using AI technology. The next aspect is focused on wireless technology. So in wireless is another means. Now few countries are adapting. Of course, EU is not adapted to, or US is not adapted to wireless technology because it's very expansive network. But small vehicles already being in commercial market. For example, the researcher Salto has developed IWM system, which is available for small applications where the power from the wheels will be transmitted through cables, which is a standard model, and store the energy in the vehicle because we use the running condition for storing the energies in the battery. So the development from Salto is through two coils, which are the transmitter and receivers, which is nothing but an isolated transformer, through which we can able to transfer the power during the running condition to the batteries. Or of course, we can create on this model with wireless charging network, but the efficiency comes down less than 85%, which is a big trademark, I can say, questionable with these technologies because efficiency is very poor. We can't able to have a huge air gap. So that's also another big challenge in designing a wireless power transfer system for charging and of course for storing the energy during running conditions. So this model is readily available in the commercial, but for very low power applications and not for high power train. So if you look at hybrid electric vehicles, so hybrid electric vehicle has its own challenges because we are going to have a fuel tank, engine, and then we have a generator. It has to be coupled to a rectifier, which is a power electronics converter. Then we have an additional network, which is coming from battery chargers to the battery, then to your DC-DC converters, and they are coupled for the motor control. Then we are talking about traction motors and mechanical driving systems. So as I discussed in the previous slide, the problem is associated in coupling these mechanical unit and electric unit at present is a big challenge. That's why all these hybrid electric vehicles are having only 68% efficiency, even though the running condition is very cheaper. So that's why these models are not very popular among the developed countries at present because of the efficiency which they produce only 68%. So I can say about the limitation that's most important about these hybrid model of electric vehicles. They are limited with, for as I said, large traction drive system is not possible. Large control algorithm is required. Adoption of AI technology is very complex, and multiple storage energy conversion is required, which is also a loss of energy in the entire complete network. But we have some future advantages because they have optimized power plant, possibility to have modular power plant, and of course, there is a possibility to shift black box service exchange. So this is very important safety measure in hybrid electric vehicle, which is not possible in case of battery based or absolutely a combination of ultra capacitors and batteries. So this is a mature technology, can be used for a long time, fast response, and there is no emission in hybrid electric vehicle. But the drawback, as I said, it cannot be applicable for very large power transmission systems. We have another model which is called a parallel hybrid model. In parallel hybrid model, it's like a general concept. We operate two power systems or mechanical and electrical power systems in parallel operation. So we have a fuel tank, engine. Parallelly, we have battery units controlled by power electronics units, and we are coupling and we create a mechanical transmission systems. So in this case, what is the problem? We are operating at a parallel operations. The capacity of current carrying capacity of both IC engine as well as from the battery unit should be the same. Obviously, this is a big challenge in parallel, so that we have to have both capacity in same. As I said, the limitations, they are very expansive, complex control. And again, it is a combination of mechanical and electrical. So we need to find a proper algorithms to adapt AI technology to ensure complexity network under failure conditions and safety measurements. And about efficiency, it requires very high voltage to ensure high efficiency. That is a big problem. So in case of electric vehicles, we are restricted to with battery with 48 volts. Of course, with IC engine, we are going around to near to 2000 volts for a commercial small power electric vehicles. But this is a big challenge when we are coming into parallel hybrid electric vehicle. But what is the advantage? There is no emission, economic with respect to the gain when compared to series model, because we have a high current, so that high pollution is possible. More flexibility is available because it's parallel connected. Even if one power supply is not available from the battery, still we can run the system with IC engines. And about the comparison, you can have a look how parallel and series works. So in case of parallel and series, we have voltage variations. Voltage variation, you can have a look in parallel. We can have between 14 volt to 300 volt, whereas in series combination, we have 216 volt to maximum 900 volts. So we can have a complete variation. Power requirement, we can go up to parallel 40 kilowatt, whereas in series, we can go up to greater than 50 kilowatt. Relative gain is very important. We can go up to 40% efficiency in parallel and 75% in series. Other possibilities, we can go for a combination of series, parallel, hybrid electric vehicle. We can combine both systems. This is a simple example how a planetary gear wheel system is used for energy storage technology in hybrid electric vehicles. In this case, we combine both series as well as a parallel transmission of power, and it is shown here. So we have a battery unit. Battery unit controls the motor controller as well as it controls the generator. And of course, the planetary unit, which is shown here. So in this way, we can have a combination. We can able to combine both series and parallel by using this planetary gear system. And we can have a parallel operation between series hybrid network and parallel hybrid network, so that the efficiency might be increased, but the cost is very high. So this is an example how it's been done. We have a battery units to a battery controller. Then we have lock units to control the transmission networks. And another part, we have a motor controller again for the traction motors. So it's a parallel operation on either side, and we are controlling the electric vehicle effectively and for a better than hybrid and series model. We can also look at complex models, which is commercially available from a company called Toyota. And this company is from Japan. This is also find a suitable high efficient power flow. So they have two different modules, which is like a split CVT system and compound CVT systems. Both the cases, the slight difference is the application part of view. For example, in case of split CVT systems, we have powered split devices, which controls the final drive to the vehicle apart from the electric motors parallelly, and of course with the storage energy systems. In case of a split CVT system, the power is split between the mechanical part and the electrical part, and finally coupled towards driving the electric vehicle. So this is a difference, but this is the most successful model from Japan company and commercially available, and we can go for high power system. So this is the most adapted system in Japan. So this is a general model how all these systems works in electric vehicles, because we use different networks. So obviously we have different braking networks, motor control. All these are controlled from the battery, which is a primary network with voltage operation of 48 volts. So you can have an idea how these batteries are controlling different networks in an electric vehicles. The most important is the storage energy, because storage energy plays a critical role now because of the cost of the battery. And these all standardizations are given from Advanced Battery Consortium from United States. They have some guidelines to use the battery. So the primary goal of the battery, the most important is the energy density, which is around 135 watts per L, because for the midterm and for the long term, it should be 300. And the most important is the fast charging, which is going to be the future. For about midterm, we can't go more than 0.25 hours. It's a maximum possibility. Still, the standardization is not available for long term. This is a big problem for batteries, and these parameters has to be governed. And the most important also is the cost. The cost is around less than 150 USD kilowatt hour, whereas for long term is less than 100. So you can see the difference, how much expensive the battery has its primary goal. And about the life cycle, that's most important. Lifetime for a midterm is only 5 years, where long term is 10 years, then we have to replace the batteries. So it's not a permanent solution. Secondary goals about self-discharge, which is less than 15 hours for a midterm, in total of 48 hours percentage. And for long-term vehicles, which is less than again 15 in terms of months. Maintenance, the crucial importance of the battery, we don't want any maintenance. Thermal loss is very important. Thermal loss, which is around 3 kilowatt hour, is the standard for the electric vehicles. And about lead acid, we don't want to look at lead acid because lead acid battery is not commercially used for electric vehicles nowadays because of the it's hazardous to the system. It's not well protected. So we are not much interested in lead acid batteries. The future, again, we are looking at nickel metal hydride batteries because it has a lifetime which is much greater than lithium battery, between 200 to 300 life cycles, with high discharging capabilities, and you can able to reduce more memory effects, which is controlled by control algorithms. So we consume only less memory of the processor. And advantage, it can be a double energy density when compared to lead acid. There is no arm loss. Recycle is very easy possible. Technology is readily available. Safe operations, and of course, it's used for longer time. Lithium ion currently we used in application, very expensive, and lifetime is restricted. And still now we don't have a recycling capacity for lithium ion. And about other possibilities, we have zinc, nickel zinc batteries. This is also another future we are looking at. Most important is the temperature, which can operate between minus 10 degree to 50 degrees centigrades, and user friendly recycling technologies are introduced. High power density is available, high power energy density is available, and doesn't produce any effects like other batteries. And comparing to lithium ion battery, nickel zinc is not very hazardous in nature. So even the residue will not cause any environmental pollution. But there is a drawback. Every system has a drawback. Preventing the use in electric vehicle because of the fast growth of dendrites in nickel zinc battery. That is one challenges we have to overcome. Other possibilities in energy technology is going to be nickel cadmium battery. Nickel cadmium battery is having much long lifetime, and they are fully charged even from zero discharge condition, not like lithium ion. We have to control the state of the charge. And the major problem in this case is the cadmium, which can pollute the environment, and disposable is a big challenge. So again, it's little expensive than a nickel zinc battery. So we have a prominent solution to overcome the problem of lead acid batteries, and of course lithium ion batteries. We can use these all combinations to overcome the problem of lithium ion and lead acid, so much cheaper. Of course, there is another option called lithium polymer in the future. The technologies are working. Few vehicles are available in countries like advanced countries where they use a lithium polymer. These are the comparative solution. I can give you an idea how we are working on different batteries. So we have current models i3, C30, B-class, C6, and RAV. If you look at the close combination, C30 has a good efficiency, which is around 95%, which usable capacity of 22.7 kilowatt hour, whereas E6 as a maximum goes to 57 kilowatt hour usable energy, and efficiency is 90%, 93%. So it's a trade-off between C30 and C6 model. If you are looking at more efficiency, C30 is the best model. C6 little less efficiency, 2%, which is not a big questionable, but the storage energy capacity is 57 kilowatt hour. And as I said, in the future, to reduce the cost of the battery, we have a prominent solution: ultra capacitors. Ultra capacitors are adapted in all forklift companies in United States, of course in Europe, because it's very cheaper. It's like a capacitor, 2 layers are separated by a medium, and it's like a standard capacitor. Manufacturing cost is very less, and we don't want to worry about the state of the charge as like a batteries, and it's cheaper price, long time. Most important, can be powered from AC grids or DC grids, so doesn't have any problem with the grid application or standardizations. And the big problem is sensitivity, because a small change in the current peak values or ripple factors, it can damage the capacitor, because this is another research which goes at a larger scale, the reliability of capacitors. So reduce the cost, we can use in parallel combination batteries and ultra capacitors, and we can pump to the load of the electric vehicle. So a large current can be driven, and this can be used for a long service application and adaptable to any temperature conditions and loading effects where batteries fails with such applications. And fuel cell, as I said in the beginning, they play a critical role, because why fuel cell? There are different classification we have. We can use a PFC model or AFC model, or MCFC or SOFC or SPFC or DMFC model. So these are the available commercial utilization of fuel cell markets. You can have a complete look how they are working at different temperature. Why we are talking more on fuel cell? Because they can go up to even 210 degrees centigrade, maximum 1000. So all the space applications or rocket propulsions, fuel cell is the main powertrain, not other fossil fuel. So that's why we are focusing more, all the countries are focusing more on fuel cell because of its adaptability of temperature. Power density is very important. Estimated lifetime, if you look at consistently, they are more than 10. That's most important. The major drawback is the estimated cost. All the cases, it's very expensive, going near between the minimum value of $200 per kilowatt hour to maximum 1000. So it depends on the application and requirement. These models are commercially available for the fuel cell. Other technologies for the energy storage, which is developed by Porkies in hybrid made energy technology. They use a flywheel. So flywheel energy technology is already adapted in high power electric trains, where we don't use HVDC, medium HP, MVDC, because all these hybrid flywheels store large capacity of DC energy, and they can be pumped back to the grid, to the application. So we can avoid the batteries, but the space consumption and the cost is much expensive than the battery. Battery can be adapted in a small space, doesn't require large space requirement in an electric vehicle, but a flywheel requires large energy, but the efficiency goes near to 98%, which cannot be compared with other energy storage technologies. And these are the classification of flywheel. We have different materials, strength and cost, depends on, we can able to choose whatever the required energy. So the most synthetic material available is the composite materials that can use to have a different range of cost. And the monolithic materials are used for low power applications. This is an example how we are making all these flywheel, why it is more expensive when compared to other technologies. Finally, I can conclude with different storage. We have battery, ultra capacitor, fuel cell, and flywheel. You can compare. Most important is the energy density and power density. So battery has a very high energy density, power density is low. Ultra capacitor is just vice versa of the battery, and fuel cell has very high energy density. Again, the power density is low. Flywheel. So this is a combination. So that's why in the future we are planning more for the cost optimization, fuel cell and battery, because one is giving more high power density and low power density. So this is a combination. We are looking at different electric vehicles for the combinations. And the most important is the commercially available vehicles. So battery, it is most dominated by Tesla and Nissan. Fuel cell plus battery is dominated by Toyota and Honda. Flywheel is dominated by a company called Porkies, which is the only company which manufactures all these electric trains, which uses flywheel. But now they are focusing these flywheel also for commercial electric vehicles for home application. About the power consumption is very important, because the motor play a critical role. If you are using an induction motor, and the maximum speed we can go up to 12,000. SRM motor we can also go up to 12,000. BLDC motor up to 9,000. And what are the types of electric vehicles we can use? Either we can go for hybrid electric vehicle or battery based electric vehicles. And there are some standardization of power. You can have a look. The standard powers guidelines given from Road Consortium of United States. And about torque density is very important. If you are using a permanent magnet motor, the torque density, you can have a look how much percentage per copper mass is used. Of course, induction motor 6.6, SRM motor 6.1. So that's why all electric vehicles in the market are using permanent magnet motor, not SRM or IM motors. They go more completely towards brushless DC motors or permanent magnet synchronous motors because of high torque per copper mass. And about charging station, that's most important. We are looking at fast charging stations. These are the guidelines already amended for from the Society of Automotive Engineers from United States. The same guidelines is used in all the countries. Only the power range varies, because in United States they use 120 volt. In India we use 220 volt or 440 volt single phase or three phase. But for the commercial application, the current carrying capacities and braking all the same, nothing changes. For level 1, we are having 120 volt and the current ranges from 12 to 16 amperes. For maximum current, breakers needed to be designed between 15 to 20 amperes, and output power ranges maximum 1.44. Level 2, the voltage varies between 208 to 240 volts. The current ranges from minimum value 16 to less than or equal to 80 amperes. And for 80 amperes, still the guidelines is not provided by NEC. And output power varies from 3.2 maximum or less than 14.4 volts. About level 3, we can go up to 600 volt high power, and the maximum current is 400 ampere peak, and the breaker requirement is around 150 amperes, and output power is maximum. We can go for a single vehicle 3 kilowatt. DC power station is going to be the future, because all our batteries, we are having three levels. The levels varies from 200 volt to maximum 600 volts. Current carrying capacity varies between less than 80 amperes to the maximum value of 400, and power varies from 36 kilowatt minimum to a maximum 240. So these are the standard scales when we are designing an electric vehicle charging stations. And about a wireless charging station, there are many solutions available. At present, we are in China, they are adapting online inductive power transfer, which is called OLPT. Efficiency is minimum, EMI is very minimum. The frequency variation can be done between 10 to 50 kilowatts. The cost is very high, volume is very high, complexity is very high, but the power level also goes to very high. So this is the technology at present China is implementing for wireless power transmission. Other technologies we have based on inductive power, capacitive power, permanent magnet power, and of course the resonant converters we use. So in technology they say resonant antenna power transfer is actually a resonant converter. So in all the technologies, the power comes to very medium or very low. That's why China has adapted OLPT technology. I have some more slides, but this is time consumption. I am unable to show you. We are also working on some concept on these technologies with power electronics converters, but the efficiency, of course, the cost is the big challenge. And this is a generalized model how we are looking at the electric vehicle in the future. We are not looking only to drive the motor. Of course, we need to have a common DC microgrid within the electric vehicle, which can couple between the existing electric utility grid and the electric vehicle. So it can be a bidirectional power flow from the energy storage devices within the electric vehicle to the grid, or within the electric motors of the electric vehicle by power electronics converter through DC-DC converters. So we can pump the power from the energy storage to the motor or to the grid, or of course we can pump the power from the motor to the energy storage devices through all these control networks. About power electronics converter, there are many power electronics converters used. Of course, these are called universal DC-DC converters, but they are limited with efficiency because we are combining a buck converter and a boost converter, and the switching losses are more and gain is limited. And this is the new configuration developed from ISG Bangalore from Professor Gopakumar. So he uses two different inverters connected across an open winding and control the battery. But there is a flow of I can say, for example, if there is an untechnical persons, high frequency signal or passes through these winding, which creates a lot of oscillations and efficiency and heating in the system. To avoid this problem, we can split the battery into two networks. Even one battery is failed, we can use another battery to power the motor. So in this case, we can have the power 50% under faulty condition, and we avoid all these high frequency noises passing through the winding. So overheating is not produced. The system is very effective. Other possibilities, we have universal power factor control converters, which powers the batteries. A combination of two different boost converter. Again, the gain is reduced because of these conducting devices. We have reduced efficiency goes to 84%. Other possibilities, we use a universal bridge power factor control. We can control the power factor on the input side, but the devices are only half cycle. It's not fully controlled. So the efficiency down to 50%. The same structure, we can able to increase the number of legs to 4 legs. We call it as an interleaved boost converter. We can able to maintain the power factor unity on the input side of the grid, but still the power controlled in each legs. In a simple language, I say only 50%. Again, even though if we are increasing the legs, the energy delivered to the load or the current delivered to the load is reduced by a factor of 50%, which requires a large capacitor. The future technology we are working more on electric vehicle is wireless. So this is a standard model. On the input side, we have a high frequency inverter. On the load side, which is an onboard converter, which is an uncontrolled bridge rectifier, which is a cheaper solution. At present, all the companies adapted in electric vehicles. Since the ratio of the design of the transformer, which is in a wireless network, in the ratio of 1:n, the complete power available from the uncontrolled bridge rectifier will not be delivered to the battery unit because they are uncontrolled device, and it divides by a factor by 2. The capacitor requires very large. The future technology is focused on paralleling multiple converters to enhance the high current on the load side. So one of the prominent solution at present all the companies are looking, but still the future will be focused on controlled network on the secondary side. Other possibilities is to enhance the high power by adjusting the transformer. Here they are introducing an LR along with a series capacitor, resonant capacitor, which is not visualized here. By introducing these resonant capacitor, the more energy can be delivered to the secondary side on the onboard network of the electric vehicle, and we can pump more power. Also, in this case, the challenge in the future is going to be replaced by controlled network. Other possibilities, we are looking at the parallel combination. So these two networks as a parallel combination, where we use a multiple stage power conversion from the grid to the load side power electronics converter onboard network in the electric vehicles. So in this case, we use the grid power in the primary stage, store in the battery bank. Then the power will be given to the electric vehicle with a combination of a buck boost converter, which controls the current and the voltage very effectively. And we use an additional UC capacitors to control high frequency signal can be suppressed at the DC link. Other possibilities, we can use multi-stage converters. Due to the multi-stage, we are using AC to DC conversion on the primary side of the grid connected system. On the onboard network, we are using a bidirectional DC-DC converter. So this is another feature we are looking at to pump the power from the electric vehicle to the grid. So this is the future. At present, we are working more on bidirectional communication with the grid. And these are the other possibilities. They have major drawbacks because more number of converters are coupled in parallel operation in cascaded mode. So efficiency come down. These models are already adapted for hybrid electric vehicles, which is connected in a peripheral mode with the grid. And this model is a failure model at present used of efficiency limitation. Of course, this one. And this model is a cascaded model. We are working more on the cascaded model where one side is a grid connected, another side is a battery model, which are pumping parallel to the motor. So this is the present model. Reason plug-in electric vehicles are adapted last 3 years. And there are many converters which uses for this application in cascaded model, which are shown here. All the cases, there is a multi-stage power conversion. When there is a multi-stage power conversion, every stages uses the energy by a factor. So the end efficiency connected to the electric vehicle is much reduced than 85%. And these technologies are already tried in various levels in electric vehicles. At the end, I can give you a conclusion how these converters are used. Buck converters are used for sending the power to the battery. Buck boost converters are used for regeneration action. Interleaved boost converters are used to increase the power factor on the grid side. And of course, they use only for charging. And we are using bridgeless boost converters, which can be used for charging as well as power factor correction. And the future, which is the most prominent solution, we are working on wireless power converters, which is a wireless power technologies, where we use user source voltage converters, where it used only for charging, not for pumping the power to the grid. So this is a technology which is adapted in a, I'm sorry, my control is not working. Yes, this is the technology what I talked about China, they are working. So this technology, they use high frequency converters on the grid side. Of course, uncontrolled bridge on the onboard network of the electric vehicles. So they have a special track. You need to have a special roads where there will be a conductor, a primary coil will be fixed throughout this traveling distance. And the secondary coil will be placed on the pickup compensation, we say it technically, on the electric vehicle. With a small air gap, always the power will be pumped to the electric vehicle on the track system, and it energizes all the network available in the electric vehicle. This is the model already implemented in China, but the major problem is the efficiency and very expansive model. They already tried for a commercial application and it is in progress. So there are many wireless technologies available. So inductive model is available, which uses the maximum power range between 6.6 kilowatt to 50 kilowatts. We have capacitive energy technology, which is used the capacitor as the main source of energy. Capacitor as the main source of energy, and it can be used for storing the energy technologies for a long range of applications. And these are not sufficient enough for charging applications, whereas inductive is sufficient enough for charging, whereas capacitive is not enough for charging application. Then we have PMT model, which is also having much advantage when compared to other models, because we have a minimum distance for 150 millimeters for charging between the transmitter and receiver coils. And this model is well defined model, but the major disadvantage, it produces a lot of vibration, noise, and lifetime is limited. The last one is a prominent solution. We are working more on resonant converters, how we can adapt for a wireless technology, and we can go up to a minimum distance of 40 centimeters, which is a pretty good application when compared to others, because 40 centimeters is a very limited air gap where we have reduced EMI effects and high efficiency and high frequency. In the future, if you are looking at the wireless technology for charging networks, obviously resonant inductive power transfer will be a key play. Other technologies I already talked. Online power transform is already implemented in China. As I said, this model has a very expensive model. Other than that, it's commercially available in that, but efficiency goes down below 85%. Other possibilities, we have a resonant antenna power transformer. This is also another prominent technology. We can increase the distance up to 10 meters. 10 meters is the difference between the transmitter coil and the receiver coil, and it can be adopted in megawatt range. Still, the system is under testing, not available for commercial application. With this, I like to say the future, how the future will look. The future is looking for various commercial application as the point of unidirectional VGC, vehicle to grid communication. So we have auxiliary services in the case of V2G. And in this case, power electronics converter play a critical role by connecting the electric vehicles and the grid. The limitation is service range. Advantage, we can get maximized profit, power loss, cost is minimum, and emission free. Bidirectional is very important. Bidirectional is the future because we are going to communicate from the vehicle to grid and grid to vehicle. In this case also, the benefits attains. We can have a maximum profit, maximum power, minimized cost, less efficiency. Grid will not be overloaded because it's a bidirectional communication. There is no any failure in the model. Of course, we can maximize maximum renewable energy systems. Limitations, battery degradation is a big problem. Hardware developments for such bidirectional communication is complex. Capital investment is very high, and there are social barriers because it cannot be adaptable to all countries because of the different grid network. Services, what we can have different services. We can have a load leveling, peak power sharing, we can able to do active power control, reactive power control, voltage regulations. Harmonic filters can be designed very effectively, which is a challenge of all the power converters which is with the electric vehicles to the grid. And we can obviously support integration of n number of renewable energy systems. With this, I complete my presentation today. If you have any specific questions, I can talk about electric vehicles. If you have any specific questions, I can talk because it's a limited time. I can't provide you all the solutions, also what we are developing in our lab because it consumes a lot of time. Any questions?
So what is the impact of that wireless charging cell electromagnetic effect? What will be for human? What would be the restrictions, sir? Actually, we are not working on. Since we are working at very high megahertz operation, we don't have any effects because we have EMI filters, as I said, in all the cases, because we have experimental results on these technologies also. So we don't have any EMI effects which is going to affect us because very strong filters are readily available and doesn't going to have a huge effect on human parameters. It's not like mobile communication. So it's between a short distance between two coils.
which is maximum 40 centimeters. We are targeting more up to 150 millimeters shorter distance. So I think it's a zero effects on human effects. Maybe, yeah.
Now the present EV, whether they are employing that PM motors as synchronous motor or it is in a development stage.
Already it's commercial application. We are no more. I already explained you in my slide. We
Yes,
can't
yeah.
use no more. We can't use no more induction motor because all the electric vehicles now they recently developed. They use permanent magnet machine. No more induction motor. Either they go for permanent magnet synchronous machine or they go for BLDC motors because they are more sensitive, speed control, and high torque application. And most important is size is very small, so you can make an electric vehicle more compact.
Cost, sir?
And of course, I can give you a best example. Recently, Government of India adapted two-wheelers and three-wheelers in collaboration with Canada from a research group. I know the colleague. They developed a motor which is used in all two-wheelers and three-wheelers in India, which is a switch reluctance motor developed from their lab. So the professor Hemadi is from Canada. So their lab developed in collaboration with Indian companies, and the motor used is from Canada. So this is a SRM motor because for a commercial application, we are looking at Indian perspective, cheaper price and high power torque and high current density to store the batteries. So they choose an SRM motor as a solution because you can see here, we can go up to maximum 12,000 and the base speed is 2,000. And the most important is the torque per copper mass 6.1. So that's why they used SRM motor as a commercial model for using two-wheelers and three-wheelers.
Thank you.
Thank you, sir. Sir, one more question from our participants. Dr. Ishrat Misana, how feasible is to explore the different materials that can be utilized for flywheel battery system?
We can't use I can't say flywheel as a battery because battery we have a different technology, but flywheel, as I said in the beginning, it's commercially used in high power trains in all the countries. Of course, I don't know, particularly in India, still we are using all the diesel engines, but flywheel is a in all they use large consumption of energy, MD, because we are moving from HVDC to MVDC, medium voltage DC current networks. So in this case, these the example how a company adapted already these technologies for high power train applications. As I said, there are material used, especially it's flywheel is nothing but another generator. It's like a commercial generator, but the technology used to store the energy. It's a simple concept of regenerative energy. If there is a technical person, you can easily understand. Those who are coming from electrical background, we have a regeneration power in any electrical machine. It can be an induction motor or synchronous machine. These regeneration energy needed to be stored. The same concept is used in a motor. Then we use different material. We are using monolithic material or composite material. Based on the material, we can be able to reduce the cost and of course the energy density, maximize the energy density. So that's why these technology is used in energy storage when compared to the battery. Drawback, as I said, it consumes a lot of space and heavy.
Okay, sir. Thank you, sir. So one more question, sir. What is the one more question from video? What is the advantage in Tesla battery?
For example, Tesla batteries, all the batteries now we are working on electric vehicle use lithium 100% because it consumes less space, energy density is very good, and controlling lithium battery is very effective with control algorithms, but the cost is very high. Still, there are cases in Tesla batteries, explosives happening. Even the guarantee is given for 99 to 98% safety because of the temperature adaptability. Because same batteries which is used in United States under different working conditions cannot be adapted to our country in India because we have an extremely hot condition. So these limitation is the big problem for adapting these battery technologies. That's why we are more dependent on China for importing these batteries. So because we are not having our own indigenous models, so battery design develops based on country requirements on their temperature parameters. So Tesla, they use batteries, but still it's not a prominent solution.
Okay, sir. Thank you, sir. So, and then one more question, sir, our side. Actually, right now we have mentioning charging systems in different level, level 1, level 2, level 3. 3 different levels and different voltage levels also. The maximum current, branch circuit, output current. How long period it will take for the charging for the single battery system? And which system is AC system or DC system is best? Which one is best for charging?
At present, no country has adapted DC microgrids. It's a future plan. All we are using from single phase AC or 3-phase AC for charging all these electric vehicles. So in this case, now we have only plug-in electric vehicles. So the single phase AC power supply from the grid or from home is connected to a rectifier, which converts these AC into DC, and putting a large capacitor, we are charging the battery. The minimum charging capacity at present is not less than 30 minutes. 30 minutes is standard. Single battery.
Okay. This will not affect our grid also, actually. Is it right, sir?
We are pumping the harmonics to the grid. Yes, we create reactive power and that is another scenario. That's why in the last presentation I said we have to control bidirectional power flow, V2G and G2V.
Yes, sir.
Sir, one more question from our Sir, one more question from our next speaker, Mr. B.B. Mehta, sir. He is asking how hybrid will use RE power.
RE, renewable energy is talking?
Yeah.
What I understood is that, sir, what I understood is that in a hybrid model of electric vehicle, we use the fuel to generate the DC power, and the DC power is once again used to run the show. So probably the entire theme and world is switching over to the renewable. So how the hybrid model of the EV will able to use the RE power, sir? Because they're using the fuel and IC engine.
Actually, in Denmark and of course other countries, we are focusing on, I mean, even for the Indian scenario from our country, the most simplest solution in the future will be converting all petrol station into charging station. So we should not depend always on the grid, because as the previous question, when we are connecting more renewable to the grid, more power electronics convert to the grid, we have many problems like voltage swag, swell, reactive power compensation, and of course we'll have resilience. To avoid these problems, the major scenario we are focusing on DC charging station, where the power requirement for the DC charging will be from the local. For example, in case of Orissa, we have a lot of rainfall and tidal power generation is very good. So we use the tidal energy for all these charging stations. For example, the places where we have more sunlight, we use photovoltaic systems to generate them. For example, Gujarat is the best place. They are the most high power generation of photovoltaic power in the entire country. For example, in Tamil Nadu, we have Kanyakumari, which generates more wind power. So we know each location, we have maximum power, which is generated from the local community. And all these DC charging network developed based under the Society of Automatic Engineers is to develop within the local availabilities, not to connect with the grid. So when you are not talking with the grid, all are islanded mode, technically we say, when we have all these power charging unit with islanded mode, then we'll not worry about spoiling the grid or integrating with all the renewables. So there won't be any problem with hybrid model. So when there is a more power from the renewables, we connect all these DC microgrid charging units from the local network of the renewable energy. This is happening in Denmark. So in Denmark, they use 45% of windmill power for all applications. When there is a shortage from windmill, the main grid power will be connected. The main grid power will be from, say, a very few percentage, like 10% is from the coal. So they use the power for the compensation. So in this way, it is operated in hybrid mode, and they keep the electricity market 99.9% stable. So this is also possible in our country when we are looking at local energy availability. So we have to use very effectively the local energy availability for local needs than for the common grid.
Thank you, sir. It is a very informative and useful session, sir, to the students, research scholars, and professionals also, I think. And
Sir, I have one question.
Point to that our mail ID, sir. I will share to you already. And any questions from our participant side, sir? Any others?
Hello, sir. Siraman here. Sir, I have one question. Can you give some insight about power electric power electronic converter requirement for a vehicle to grid mode of operation?
Yes, today I didn't show you some important slides because it takes a lot of energy. This is a commercially available different modules, which at the end everybody use uncontrolled bridge rectifier, but these models are tested under different condition. As I said, this is the combination. I show you a universal DC-DC converter, which is a combination of if you are from power electronics, it's very easy to explain. It's a combination of a buck converter and a boost converter in a parallel operation and enhance the current to the grid. The disadvantage, we can't operate these devices more than 75%, and the efficiency comes down less than 85% because of cascading of multiple converter, even though the current is very high. So other possibilities, we are working on permanent magnet machines with isolated converters. Can have a look. So one battery can pump both the side and we can enhance the power. But if one side of the converter fails, it becomes an open circuit, the complete propulsion stops. Other problem, we inject high frequency signals. So these are the simple models and we need to compensate. So to avoid this problem, we are splitting the power. And as I said, there are grid connected applications. We are using interleaved boost power factor converter. So we are controlling the power factor with the uncontrolled bridge rectifier to keep unity power factor on the input side. And on the load side, we use a multiple boost converter and in cascaded mode. So in cascaded means parallel. In parallel, current will be very high and you control the battery. So these are some example. If you want to look at the recent modules, we are figuring out with a resonant converter where we have wireless transmission transformer or isolated transformer or tank circuit, whatever we call it as, and by which we can able to communicate between the grid and of course the battery. When this converter become controlled network, at present we are not using controlled network, we are using diodes as a onboard chargers in the electric vehicle because it's very cheap. You know, a 3-phase bridge rectifier is very cheap. But when you are controlling with the uncontrolled bridge like MOSFET or IGBT, then you need additional control units and you need to compensate all the ripple content, etc. Then work is tedious, but you get more freedom to control between the batteries and the grid. Do you got my point?
Yeah, yes, sir.
Yes, sir.
But this is at the point of I'm talking with electric vehicles. If you're going to talk with the grid to the power, that is a different scenario. We call it as grid connected converters, where the converter of a 3-phase converter in multi-stage, we can call it as AC to DC converter, or we can use directly the inverter to communicate with the grid done to the electric vehicle. That is a different scenario. This is a scenario I'm talking with respect to the electric vehicle to the grid communication.
Yeah, okay, sir.
Thank you, sir.
Sir, one more concept also there, vehicle to building. So the similar type of converter requirement is used for that also?
Yes. The converters are the constant. We are putting into different application based on the requirement. So we have different converter modules. I showed you here. So we have different converter modules. So in converter modules, they are placed with the grid here. So depends on your requirement. For example, I'm not a very commercially modeled guy. I don't want too much investment on putting a converter. So we have different models of converters development for grid connected systems. We have different converters. So based on the consumer requirement is efficiency, EMI-FX, fast interaction, etc. We can choose appropriate power electronics converter to be connected between the grid and the battery. So it depends on the commercial requirements.
Yeah, okay, sir. Thank you.
Thank you, sir. Thank you, sir. And
but the
thank you for
prominent
the
solution, prominent solution, as I said, this is a prominent solution. I didn't show you this slide because of time restriction. We are also working more on this for electronics converter. We have separate slides for that to explain how we develop and how we are testing in the laboratory. So you can look at the efficiency. Overall efficiency is going to be 88.8%. Now you can able to communicate between your electric. This is an onboard network. So this side, the secondary side, is an onboard network on your electric vehicle, and this primary side is the charging unit. So you can able to communicate from the or electric vehicle towards your grid. And each stage we have shown how the power is being developed. So 3.28, the standard power we develop in our lab. This is an experimental test we conducted in our lab. So 3.28 kilowatt but at the end we are getting only 2.91 kilowatt. So there is a various losses in the stages, and the efficiency goes down to 88.8%.
Thank you, sir. Ramesh, sir, anything, sir, you want to?
Yes, Professor Sanju, thank you so much. Even in your very uncomfortable situation, you again given the opportunity for us to have your interaction with all our participants today. Thank you so much, Professor.
Thanks, Professor Ramesh. To see you after a long time. I'm sorry, I have an internal problem here. I can't be able to turn on my camera.
Yes, no
nice
problem.
to see you after a long time. It is always my pleasure to involve with IGEN. I came here today only because of Professor Ramesh, IGEN, and Professor Sendil Kumar for his invitation. It's always my priority.
Thank you. Thank you so much.
Thank you, sir. Thank you, sir. Sir, share your PowerPoint to the ladies, please. Yes.
I will share you this PowerPoint. No problem. Thank you.
Oh, okay, sir. Thank you, sir. Thank you, sir.
Thank you.
And Janasri, please introduce our next speaker. Anil Thomas sir is waiting. Please kindly.
Yes, sir, sure.
Yes, please. And before that, thanks.
Thank you, Sanjay Kumar, sir, for making the session more interactive and informative. Thank you, sir. Next, I would like to welcome our second case, Mr. Anil Thomas, sir, who completed his BTech in Calicut University. He formulated the short-term and prospective plans for development of the electricity system. He specified the technical standards for connectivity to the grid and specified the conditions for installation of meters, transmission and supply of electricity. He collect and record the data concerning the generation, transmission, trading, distribution, and the utilization of electricity and carry out the studies relating to this grid generation. He coordinated the planning of maintenance of generating the machines of various generating companies of the region, including those of interstate generating companies supplying the electricity to the region on an annual basis, and to undertake the review of maintenance program on the monthly basis. Of course, there are a lot more to say about him, but with this short intro, I would like to hand over the session to the engineer Anil Thomas, sir, who is the head of PSP, to light on the topic of battery energy storage system. Welcome you, sir.
Well, very warm welcome, Anil Thomas, sir.
Thank you, sir.
We thought of meeting you. And unfortunately, we can't able to do. Maybe hope next your visit to Chennai, we will have a very strong collaborative meeting.
Yeah, sure, sir. Sorry for that. Sir, Sir Senthil, sir, can you just put up the slides? I'll just quickly go through that. Yeah.
Okay, sir. Okay, sir.
I'm just stopping my video for better connectivity for everybody. Yeah.
Is it visible, sir? Okay, sir.
Yes, sir. Yes, sir. Can you put it in the slide mode and just we can go to the second
please,
slide?
Yes, definitely.
Yeah, first of all, I'll just thank IGEN team to give me an opportunity to speak about the topic. I'll just quickly take you to the more of like a management background of the BESS and how BESS will revolve in our coming years. So I'll just go to the next slide. So we can just, thank you, sir. So before just getting into why battery storage is required, so I thought that it is more important to understand that how energy transition will take place. This is a model which DNV has developed, and it is a global model where we come up with the plan that how our power system, not only power system, the entire energy sector where how we consume energy, not only the electricity, will transit. So if you see on the left one, which is on the 2018 model, how 2018 model, the population across the globe utilized the different forms of energy. So you can see that the source of primary energy was oil, coal, natural gas, biomass, and very little of solar thermal, geothermal, very little of solar PV, hydropower, nuclear, and wind. So these three were either these all primary source either were directly consumed or were consumed through the energy conversion, that is for power generation. So in the 2018 model, you can just see on the right side, in that we have three major sections which we have divided, that is transport, manufacturing, and the building. So the subset of the transport, which is road, maritime, aviation, rail, And in the manufacturing, you can see the base metal, iron and steel, and feedstocks, and there's such things. And in building, it comes cooking, appliance, heating, electricity, etc. So if you see that in the 2018 model, or which we have historical data, we can see that oil played a major role predominantly in the transport sector and in the road, where EV will come and it will convert this oil into electricity. The second is the coal, which where predominantly it was consumed for electricity and certain part in the manufacturing industry. The same applies for the natural gas. And then the other renewable sources like solar and wind were playing a very small role in power system. So what was happening is that the entire energy requirement, around 20%, was converted into electricity and used as electricity. So which was only around 27 petawatt hour per year. Now, what we focus through our modeling exercise, we feel that by 2050, 60% of the 60 petawatt hour will be consumed through electricity, which will form the 40% of the total consumption. Presently, we are 20% we are using through electricity. Now it will grow to 40%. And in that 40%, you can see that a major role will be played by solar PV and wind. You can just see on the 2050, the right side, the yellow solar PV has grossly increasing with wind and little bit more of hydro. So what we can see is that renewable industry is going to enter drastically into the energy supplying mode, where 62% of the entire electricity will be delivered by renewables. So out of the total of 100% of energy requirement, 40% will come in through electricity. In that 40%, 62% will be from renewable. So a huge energy injection will be through renewable. Now the problem with renewable electricity is that it's uncontrollable, undispatchable. So it cannot meet the electricity requirement of the population when they want. So there comes an issue of storage. You need to store electricity and then deliver it when the population requires for that. So that makes it very important that this ambitious plan in 2050, where will be depending on renewable, cannot be achieved with a very high quality storage system. So can we go to the next slide? Senthil sir, can we just go to the next slide? Yeah, thank you, sir. So if we just take it on the Indian subcontinent system, we can see that in 2020, we have predominantly coal. Definitely, it's assumed that coal will have not much, but little bit more installed capacity coming in, because we cannot throw away coal because of its capacity market, which it supplies, or it gives the dispatchable power. But from 2020 onwards, lot of solar PV and onshore wind will take over, with some more capacity getting added in hydropower. The major reason of hydropower capacity being added, because presently battery is not a viable solution to give a large scale storage. So people are still thinking about hydropower, and one of the pumped hydropower, closed loop pumped hydropower, is something which is being investigated across India for giving large duration storage, because the other storages are either very expensive or they can be used for the short duration. So considering the supply generation mix, which is expected by 2035, with a huge combination of solar, onshore wind, a little bit of offshore wind, very little, because even now by 2035, it is assumed that the offshore wind capacity, the levelized cost of electricity may not be less than 7.5 rupees. So that still will be expensive. So it will be a solar and onshore wind dominated electricity market in India. So to integrate this huge renewable energy, we need a good quality storage. So that brings it to the whole topic that why BESS is become a hot topic here. So can we go to the next slide? Yeah. Now, when we talk about the electrical storage, I'll not go much into this because this is a very whatever detailed we need to discuss about this. But we can just say that the storage is predominantly divided into three categories: electrical, electrochemical, and mechanical. But presently, it is totally mechanical pumped hydro, which we see as a long duration storage. And now lithium ion battery system is coming into the grid. There is around anticipated 700 megawatt of batteries will be installed in India in coming 1 or 2 years. So this is the two technologies where people are looking into a storage solution. Others are not so much fascinating or interesting as of now. So this will be lithium ion and the pumped hydro who will be leading the electrical storage system presently. Yeah, can we go to the next slide? Yeah, so what we are seeing that yes, pumped hydro will be a predominantly, they will play a major role in the integrating of renewable, and lithium ion will play, but lithium ion as presently it is very expensive and it is a very short duration storage. There is a requirement of a long duration storage, which many great scientists will definitely come up with some certain solution where by 2025-30 we may expect that this may actually overtake the entire grid storage system. So this is an anticipation which has been done by DNV, that how that long duration storage is much required, which should be there to integrate large scale renewables. Yeah, next slide, sir. So coming to the specifically to battery technology, we have just came out with an outlook. Presently in around 12.65 gigawatt of battery is being installed across the globe. And because of COVID and all those things, the installation capacity has not increased, but we think that it will increase. And in coming next decade, China, US, UK, South Korea, Australia, and Japan, they will be the major market for battery installation, and that will be followed by India beyond 2030. So India will also have a lot of storage coming up. It is just the cost of electricity with integrating of battery, which will be the driving force where India will also start depending on a lot of renewable when a lot of renewables comes into the picture. Yes, the next slide. So if you go by the zone geographical area wise, India presently has 700 megawatt. By 2025, it is assumed that around 700 megawatt of battery will be there, but that's very small considering the renewable integration what we are anticipating. Middle East and Africa, they are not into renewable as of such because of they have that abundant source in the in the form of gas and all those things. So unless renewable integration does not picks up in Middle East and Africa, battery storage may not find a major application in those regions. Australia is one of the place where and they are going very fast with battery storage, and it is assumed that they will have 3.5 gigawatt of capacity by 2025. And the southern part of Australia, where a lot of batteries, and they have a big deserts where they are planning a lot of solar panels. So that should pick up the business in Australia. Europe and not as fast as US, but still they are following US model, and Germany will be the top one with a lot integrating a lot of batteries. US is the leading in this because they have a lot of renewables, so they understand the importance of battery. So they have already installed 2.5 gigawatt by 2020. They have brought a lot of policies, initiatives, and pathways to ensure that a lot of storages comes in their country. So that's what US is leading, and then it comes the European Union, then Australia, and India is picking up and that will be very much required if we have to achieve a 450 gigawatt by 2030 plan. Yeah, next. So predominantly what all BESS can do, if you see the right side chart, we can just say that the bulk energy service, which is one of the major issues which we see with renewable integration, because when we want power at that time, renewable may not be available. So we need to store and energy time shift we have to do. So that's a major place where battery will find its application, apart from ancillary services where the battery can charge, discharge, which follows the load curve. They can be used for primary response and giving synthetic inertia for a frequency response. They can support as a secondary reserves and spinning reserves. They can support the voltages whenever required. They can even charge a dead bus, and hence they can be used for a battery black start. In transmission infrastructure, they are not very much financially viable presently, but in future, if we have a renewables connected, where the peak and the average PLF is very less compared to the peak generation, so for relieving congestion, for differables of transmission system, they can be used, but that can only happen if the cost of the battery comes down drastically, where they can supplement by not increasing the transmission system. So that's something I think it is far away, where transmission system will find exclusively role of batteries. Batteries can also be used for power quality, where they can control the harmonics, DC current injection, flickers, and improving the power factor, which I think was very well explained by our previous speaker. So and when and then definitely when renewable integration comes, the duck curve, generation peak shaving, very high ramp rates of solar and wind to control that, the batteries can find its application. So lithium ion is one thing which everybody finds a very important role. So you can see that it has a comparison on the left table is there, where they have been compared with the various different technologies. So you can see that the lithium ion is something which can be used everywhere. Apart from that, hydro, because of their long duration energy storing capability, they are the front runners with the lithium ion for the giving the storage support. Just can go to next slide. So in lithium ion, I think where all it can be used, there are different subsets of lithium ion. So where I think lithium, nickel, cobalt is what used for grid storage, and lithium nitrate. Others are used for, there are many different technologies which can be used in, that's table is there where the application can be seen. Coming to the cost part, presently it is around $200 per kilowatt hour, or 210 or around come. That's is considered to be a bit on the expensive side. If we calculate the levelized cost of storage, it comes around more than 7.5 rupees. So that is the costliest storage which presently in India we have. So that's why battery is not finding too much of takers for that. But it is assumed that as the demand increase, bulk development comes up, the cost may reduce close to $60 per kilowatt hour by 2050. So that will make renewable integration quite viable, and that's the point where I think really renewable will play a major role. So the battery cost has to come down drastically, so that then only it will find takers, willful takers in the grid. So coming the cost breakup, how that lithium ion, why it is so costly. So the battery pack itself is around 47%, which makes it too expensive, and the conversion, OPEX, EPC, and transportation and decommissioning costs. So the battery pack cost has to come down, which we believe that it can come down with large requirements. So coming into the key players in the battery value chain, the manufacturers are basically, Tesla is a big one, LG Chem, Samsung, Toshiba. These are the major players who are into battery cells. And balance of plant, Sungrow, Denpro, these are the major companies. Large OEMs are there, ABB, Siemens, Schneiders, Bosch. So these are they play the large OEMs. So integrators are there, Sungrow, SunPower, and then the development and the ownership is definitely TSOs and DSOs who will use the services to integrating renewable in their grid. Yeah, next slide. I think, yeah. So this is just a basic architecture. I'll not go in detail to this. So there is a battery system, the chemistry involved in that, and then there is a power transformer, converters, and then the digital requirements, where they based on the grid requirement, data is transferred with the high energy management control system, and the discharge charging takes place with the converters and the storage management solutions. So they, as told earlier, that they not only store electricity, they can also get involved in supporting the grid through voltage controls, frequency response, synthetic inertia, ramp controls, and improving the power quality. So this is the basic architecture how BESS can. So BESS, definitely the major role they play is in the storage and discharging, but they can also be used for controlling the grid parameters and supporting the grid during contingencies, black starts, and etc. Yes, thank you. So I have just quickly finished it. I hope I was able to communicate. Yeah, thank you.
Participants from side, any questions from participant side?
Dr. Anil, it was a nice presentation. I have a question. Like if India is going to adopt lithium batteries for energy storage, it will be a very expensive one. But if suppose we think of some other alternatives, along combining thermal energy storage or compressed air energy storage for specific renewables like wind, you can use compressed, something like that, which is prevailing in Germany or so, because they are already ahead of us. So what is the survey DNV has made, and what is that you can propose for India in your report? Because
yeah, presently I feel that if you see in India as a country, we may be more inclined towards putting more pumped hydros. That's what most of the electricity board is doing, and presently that seems to be the most viable solution, because India has a very good potential of pumped hydro because of the Deccan Plateau and the height difference. So pumped hydro is what I feel that presently may be the main thing which can play a role here rather than any other technology, because they can give you a storage of months or for more than a season, which may be required. Because in India, what happens is the wind energy starts with pre-monsoon and ends with the monsoon. So it's between May to October. So what you can do after that, and solar is only available through the 6 to 6. So let's say take a case of January around 7 p.m. So you don't have both wind and solar at that time, and wind won't be available for next 6 months. So you need a long duration storage. So pumped hydro is something what we feel that will be the showstopper here.
Okay. Like another doubt is, how will you handle the base case loads? Because both are going to be wind and solar are going to be, wind is seasonal and solar is diurnal. So in the future, 2050, we are predicting that it is going to be 60% renewable. So which will be the base case load for you to have the stability of the power system?
Yes, madam. Actually, if you say that still we can't throw away coal, we can't throw away nuclear. So definitely they will still play a major role. That's what you would have heard in the prime minister's. There's also 2070 is we are planning to carbon neutral. But yes, base load we cannot depend on unless there is a very long duration, a long duration storage is not there. Base load has to be supplied by thermal, predominantly coal and nuclear. Nuclear, as you know, that it is not, we cannot make him dance the way thermal can to a certain extent. So the base load has to come from these stations.
Okay. And what about this power to gas technology, which is coming up in Denmark or other developed countries? Will India also have some opportunity like that?
I don't think so right now. I have to get back really, but gas is still a very costly affair in India. So and solar is something which is very cheap. So we are thinking about getting into hydrogen in a different way, green hydrogen. So green hydrogen is something which India is looking for. There are big companies in India who are investing. Yeah.
Green hydrogen meaning the hydrogen
splitting the hydrogen generating through renewable energy.
You're talking about the hydrogen. Okay. Thank you very much. Very nice presentation, sir.
Sorry, but right now, a lot of projects are initiated for the battery energy storage system. Now we also mentioned some on the 2025 only 700 megawatts only coming. Is it right, sir?
Yes, sir. Sir, yes, sir. They are incentive based installation where some incentive, but it's a pilot project. So to get it in a large scale, it should be self viable. Like we had solar at 16 rupees sometime, if you say 10 years back. So that was only by initiatives and incentive based installation was there, but now it is 2.5 rupees. So it's automatically it becomes a viable solution. So we have to wait till that when large all the utilities start using. Now it is SECI based tenders where SECI is bringing it. So it's not by itself it is coming.
Any questions from participant side, sir? Balamurugan, Dr. J. Balamurugan.
I think, sir, we can go to next one because it's already 10 minutes late.
Yes, sir. Yes, sir. Okay. Right, sir. Thank you, sir. Thank you for giving me a wonderful time to start with our IGEN to give me a wonderful presentation, sir.
Yeah. Thank you, sir. Thanks.
Thank you, sir. Thank you, sir. Thank you. One minute, ma. 1 minute, please. And this is within 5 minutes they will join due to some due to heavy rain in that Madurai area. So that's why we will take about 5 minutes only. So before on that we have to start some discussions about that today's and tomorrow event presentations. And the methods are also waiting for that next 2:15 session.
Sandil sir, you can share any of our old battery videos, Sandil sir. YouTube battery, there is a lot of good content videos are there. Sandil sir.
Hi, and I'm D. Yeshwant. We are from Narayana Group of Schools. So today, in this video, we are gonna see information about eco-friendly things. And you will watch through a role play. Let's get into the video. sir. This is Ashwin. Is it biologist Vishwajan?
Yes, tell me.
Sir, I am a biology college student. I have got a project related to trees. So, can you help me with this project, sir?
Yeah, sure. Then let's meet at Greenland at 5 o'clock.
Okay, sir. That's great.
Hi, sir. Hi. So tell me, what is the project about?
Sir, the topic is eco-friendly trees. The main content of it is that what kind of trees absorb what amount of carbon dioxide and releases oxygen. I have two subtopics in it, sir. 1. History between trees, oxygen and carbon dioxide. 2. Trees that releases maximum and minimum amount of oxygen. Trees that absorbs maximum and minimum amount of carbon dioxide.
Okay, let me explain you the first one.
The history. Let's see, how was oxygen discovered from tree? Joseph Priestley, an English chemist, carried out an experiment that showed that plants produce oxygen. They put up a mint plant in a closed container with a burning candle. The candle flame used up the oxygen and went out. After 27 days, Joseph was able to relight the candle. This showed that the plants produce a gas that allows fuel to burn. On August 1st, 1774, he discovered oxygen, and carbon dioxide was discovered by Joseph Black, a Scottish chemist, in 1750s.
The second topic, trees that release maximum and minimum amount of oxygen. Let's take top 3 trees: bamboo, banyan, and neem.
Bamboo tree is the first tree which gives maximum amount of oxygen because it produces more than 70 tons of oxygen per acre per year. A group of bamboos has the ability to release 35% more oxygen than the other group of trees. It has a reputation to live for as long as 120 years. It has its origin in China. It helps to cure illness like heart problems and cancer. Rather than the plantation area, it is found in the high-tech houses to decorate it. And banyan is the second tree giving maximum amount of oxygen. A 100-foot tree produces 6,000 pounds of oxygen. On average, one tree produces 260 pounds of oxygen. Then neem tree is the third giving maximum amount of oxygen. Neem leaves are known to be natural air filters that trap dust particles and absorb gaseous pollutants. The large leaf surface area helps in maximum CO2 fixation and produce a shield against other pollution components like SO2. Trees that release minimum amount of oxygen. Let's take two trees, pine and tamarind. Pines are at the bottom of the list in terms of oxygen release trees because they have a low leaf area index. The leaf is low and thin. Then tamarind tree because it also has low leaf area index.
Trees that absorb maximum amount of carbon dioxide is...
I guess it is teak tree.
Yes, that's right.
Teak is the tree consuming maximum amount of CO2. It absorbs 3.7 lakh tons of carbon dioxide. Then bamboo tree because it absorbs 80 tons of CO2. And the tree absorbing minimum amount of CO2 is oak tree. It consumes 48 pounds of carbon dioxide per year.
Its origin is in America, and the special thing about it is it lives for 1,000 years.
Oh, okay.
So, as you have heard till now, right? Let me ask you a question. In today's time, we are in lack of oxygen.
Yes, sir. We would have to plant the tree which produces more oxygen in the place where we live. For example, banyan tree. And we should plant the tree which consumes more carbon dioxide in the place where there is lack of greeneries.
Yes, that's correct. All the best for your project. Bye.
Thank you, sir. Bye.
As you have heard how to control the situation,
Join us in IGEN ecosystem. Hey everyone, this is Lakshita from IGEN Young Green Innovators Army and studying in Velamal Vidyalaya, here to speak about a short summary of the UN SDG Index 2020. First, let's see a glimpse about what is SDG. The Sustainable Development Goals or the Global Goals are a collection of 17 interlinked global goals designed to be a blueprint to achieve a better and more sustainable future for all. The SDGs were set up in 2015 by the United Nations General Assembly and are intended to be achieved by the year 2030. Now, let's see what's SDG Index. SDG Index is the index for the Sustainable Development Goals, that's the SDGs, which evaluates the progress of states and union territories on various parameters, including the health, education, gender, economic growth, etc. SDG Index is also called as the Sustainable Development Reports, which is nothing but SDR. SDG report of 2020 was published on 30th June 2020. The Sustainable Development Solution Network, that's the SDSN, published the Sustainable Development Report of 2020, including the SDG Index and the dashboards. The SDG Index of 2020 is divided into 5 parts as Part 1, COVID-19, the SDGs and the recovery. Part 2, the SDG Index and dashboards. Part 3, policy and monitoring frameworks for the SDGs. Part 4, method summary and data tables. Part 5, country profiles. I'm going to give a glimpse of all the 5 parts. Let's begin. First, let's start with the part 1, that is COVID-19, the SDGs and the recovery. Let's see the short-term impact of COVID on SDG goals. They are divided into 3 parts. So, SDG goal number 1, 2, 3, 8 and 10 created highly negative impact. SDG goal number 4, 5, 6, 7, 11, 16 and 17 created mixed and moderate negative impact. SDG goal number 12, 13, 14, 15, still the impact is not clear. Let's move on to part 2, the SDG Index and dashboards, one of the most important one. Let's see the top 5 countries on this list. Sweden scores first by scoring 84.7 score. Denmark comes second with 84.6. Then goes Finland and then France and then Germany. Last year, Denmark was first on this list. Now we are going to discuss about the part 3, policy and monitoring frameworks for the SDGs. Comparative assessment of government strategies and policy actions for climate migration. Grey means critically insufficient. Red means highly insufficient. Orange means insufficient. Light green means 1.5 degrees Celsius Paris Agreement compatible. Dark green means role model. Countries are ranked by their spillover scores. The more the spillover, the lesser the negative effects. Example, Afghanistan and India. Hope so you're all able to understand about the glimpse of SDG goals. Let's work hard to achieve at 2030. Thank you so much. This is Lakshita signing off. Bye.
Hello everyone, welcome back to IGEN.
நான் வரல அதனால தான் பார்க்கறேன். ரைட் சார். ஓகே சார். Good morning to everyone. Another speaker is getting some delay due to heavy rain, some connectivity issues. So another next speaker is waiting. Dr. BB Bhattresh B Mehta sir is ready. So I want to call Janishree madam. Please kindly before starting we have to introduce the profile. BB Mehta sir. Sir, shall I share the profile, sir?
Yeah. Not an issue.
Okay, sir. Right. Please, more Janishree ma'am, please.
Okay, sir.
Morning,
I would like to invite our third speaker, Mr. Mehta sir, who is a graduate engineer in electrical and electronics with a master degree in engineering with specialization in computer systems and technology, and at present heading SDG telecommunication and IT of GENDISTRANSCON. He has been associated with the power sector for more than 36 years. He is overall in charge of efficient and secure power system operation and control in the state of Odisha as Chief Load Dispatcher and Director SDG. He is actively involved in renewable energy integration, system stability, electricity market economics, open access, energy efficiency, and smart grid for power system operation, and also played a key role in implementation of supervisory control and data acquisition, phasor measurement unit, wide area monitoring system, renewable energy forecasting solutions. He has also worked as a chief engineer at SDG Gujarat for a very long period and represented Gujarat at various forums and presented many papers at national and international levels conferences. So now I'd like to hand over the session to Mr. Mehta to take over the session. Welcome you, sir.
Thank you very much. Thank you, IGEN, for giving me an opportunity. Whether I am audible, sir?
Yes, sir. Definitely.
Yes, sir. So thank you, IGEN, for giving me an opportunity to share the views. It has been very interesting since morning. I have been listening, and we had a good expert who shared the views on the battery storage things. Thomas is also a good friend of mine, and he has also shared good ideas. To this, sir, why we need the storage, that is the most important thing, is that the requirement of power is not stable. Say, if we are at the domestic user, we don't use same quantity of power throughout the day. The same thing is with other category of the user also. Now, but earlier days, without renewable, what was there? There was feasibility to deviate or vary the generation as per the requirement of power. And generally thermal set or hydro set were able to do it. Now, since last 10 years, and there has been a very fast pace at which the renewable has started penetrating the power sector. And it's good for all. Say, what is the mission behind that? That we will not have any carbon footprint to be left behind our next generation or a generation thereafter. Or we would like to avail the power without carbon. We would like to have a green power utilization. We would like to have no consumption of fossil fuel from the day ahead. So with that, what has happened? We started harnessing the renewable resources. But that anything comes very easily will come with some background challenge. And the challenge is that it is a natural resource and it is not constant. And the deviation delta, the deviation delta is very large. It's not a small delta. Rather, it is sometimes more than the base. So renewable has a very big impact that it varies drastically. As far as solar is concerned, the operational cycle is limited to 8 hours, 10 hours based on the season. If it is a summer, it is more. If it is a winter, it is less. Cloudy, it may be, the day may be there, it not shining, so we may not be able to get the enough generation. So the capacity utilization factor of the solar varies drastically from season, day end. But wind is much more prominent for the deviation or uncertainty compared to solar. But the quantum of power available through wind is huge, large, and it comes with one important word for the system engineer is the inertia. So the solar power is without inertia, this is with the inertia. It has certain rules and setup done by the CEA as far as the criteria are concerned, the connectivity criteria, field stability criteria, fault right through capability, low voltage right through capability, high voltage right through capability, etc. etc. Now coming to that, it means that now we have a Cvt where the requirement of power is largely variable and the sources of power are also largely variable. So it adds a challenge to the grid operator, the person who manages the balancing of the availability and generation in real time and in a plan. So what is need to done? Let us estimate the surplus quantum and let us estimate the deficit quantum. Some part of the time in any state, if we take the demand curve, there may be some portion where the state may be surplus. And some portion, some peak area will be there that may be running with deficit. At that time, they might have to deploy the costly power, they might have to purchase the power. So the people thought that why don't we shift this requirement to valley and peak? But you know, the requirement is not in our hand, it is with the consumers. So people thought that let us store the off-peak power and utilize during the peak hours. So the motto is there, then the requirement is generated to counterbalance the availability of the power at the needy hours and absorb the power for a storage purpose during the lean period of the requirement of power or during the lean period of the demand. So that has resulted into the need of storage. Now, many things is spoken and I have also present. Can you please share my presentation or I will share from my end? Senthil, Natarajan? Anybody from IGEN can
yes, sir. Yes. Senthil, sir.
Finally do.
Just a minute, sir.
No problem, no problem. You please do it. Meantime, say the point is that now storage is one of the badly required things when we harness the more renewable and we have no restriction on the requirement of power because the requirement deviate drastically and availability deviate drastically. And all of us know that by 2030, probably as per the Prime Minister vision and commitment, 450 GW. We shall be the renewable. It may be manifold than what the conventional power available with us today. Even I have been told the other day that we have just touched upon 100 GW renewable so far by this year 2021. Now, when it comes, it is not 100 GW throughout the day 24/7, all 96 block of the day. It is highly deviating from say 20 million GW to 100 GW or 80 GW throughout the day. So now here question lies, when I don't need the power, should I curtail the renewable? Okay, we can do so because it is without cost. But then when the need of power is there, from where should I get the power? So either we still get it from the conventional or we continue to go for a storage solution. So we'll have some talk about the storage. Actually, I have been assigned the talk of electrical vehicle. I have covered something, but what I feel that my earlier speaker has covered much in detail with all variety and he has a practical experience on the vehicle. So I will limit my talk with respect to storage and challenge thereupon. Next slide, please. And you can convert into the PPT mode, please. Presentation mode. Kindly, yes. Next slide. So this is why the storage systems are required. ESS, energy storage system. See, there is an arbitrage of the energy. The storage energy is required with respect to price of energy is less. We need to store it, and when the sell, we need to during the peak hours. And also we need to do the peak shaving. I earlier explained that why we need to do it. We need to shave out, we need to clean out the peak, and we'll have some delta component available with us to meet the peak requirement. And sometimes we need to follow the load also, load following. The responsibility of energy storage is to maintain the balance between generation and the load and supporting the load change using the energy storage. Next slide, please. It also acts as a spinning reserve. You know, there is a mandate as per the IGC, the 50% capacity of the highest operated plant should be a online hot spinning available with the dispatcher. And in case of regional load dispatch, 100% capacity of the largest unit in the region should be the on-bar spinning reserve. So this also acts as a spinning reserve because the restoration of power from the stored device is very fast, immediate, and it can be deployed at any moment of time. Apart from that, it also helps us for the voltage management, voltage support, and frequency control also. And also it addresses somewhat the power quality and system reliability also. And last but not least, very important, maybe from the segmented distribution isolated network point of view, it leaves the congestion. Say sometime what happens during the peak hour, certain auto transformer gets overloaded, some distribution transformer get overloaded. So at that time, a small battery set up to few megawatt capacity will be of a very good help to improve the congestion and immediate response can be achieved. Next slide, please. This is various type of energy store. I think my president has covered very much in detail. We will just have a large, the electrical, there is a capacitor, supercapacitor, super conductive magnet, mechanical, there is a pump hydro, flywheel, compressor, thermal, there is heat storage, electrochemical, there is a battery and hydrogen, chemical is a fuel cell. Now out of this, what happens? That lot of work has been done on battery, lot of. But if you see the result thereupon, sir, we need a balancing requirement. We need a storage in terms of megawatt, hundreds plus, not the 5-10 megawatt of the battery set or something like that. And if you see the second item, mechanical, there is a pump hydro storage. I think Anil has rightly stressed upon it. That is a need of time. So we are planning, say, 175 GW by end of 2022, 450 GW by 2030. What is our planning for balancing, sir? What is our planning for storage? Probably nothing. So that way things will not move in a right spirit, right direction. It will not keep the system balanced and intact. So we need to take a call and we need to go for a large scale balancing and storage device. And probably to me, the best one is the pump hydro storage. Because our requirement is not 1 or 2 megawatt. Our requirement is not a limited life cycle of battery. After 5 years, I have to replace the battery. We need the requirement of storage and balancing for years together, maybe more than 3 decades, 4 decades. So pump mode hydro storage is the best solution and alternative to meet this requirement. And people say it is a climate issue, approval issue. So that is all man-made issue. No technical issue has been observed so far. I have my views that rather battery storage has much more technical issues, but we are more concentrating on a small scale. We arrange a seminar for battery storage, which is of 5 megawatt. We have a hardly seminar, 1 or 2 seminar in an entire year for the pump mode hydro storage. Even if you see at the policy level, at the planning level, right from the this planning commission or that CEA, our honorable commission, even POSOCO, who is a custodian of power system operation control, did they put forward to the requirement that we need a storage solution, we needed a balancing solution of the mega scale for the 450 GW being planned by the MNRE for the next 20-30 years? No. So it has to be done. Otherwise, we will not in a easy way to operate the grid, or it will not be a commercially meaningful decision we have taken so far. I think we can switch over. What is my one certain point to convey over here is the capacitor, sir, but it has its own problem and own limitation. And I have never seen the megawatt based capacity up operative and running with a capacitor. Pump hydro is a proven thing. Flywheel still it is in a academic or research institute. Compressor is also something like that. Heat storage is not viable. Battery, people are working much working on that, and it has led to the lower down the cost of battery. But what about the life cycle of battery and disposal of battery? That has to be accounted, that has to be thought. When you go for 100 megawatt battery storage system, you have, if it is 5-year life cycle or 7-year life cycle, and you know every year the life cycle is 5 years, but the efficiency goes down. So it has to be also accounted. Right? Battery, whatever, sir, if we think very patiently, solar energy is generated in a DC, we convert into AC, we bring to the battery storage device, we convert into DC. Once again at the time of use, we convert back to AC. So the conversion losses are 3 times. Conversion losses are 3 times. So we have to take a call, and whatever efficiency we improve, it is going to have its own losses. Fuel cell is also a laboratory level only. I at least to best of my knowledge, it has not come up to the megawatt scale or the grid requirement. And specifically, if we take the requirement for the state a 5 to 10,000 megawatt, Tamil Nadu is a 20,000 megawatt grid, or as a country as a whole, we are operating 150 GW grid at any moment of time. Next slide, please. I request next slide. Whether am I audible?
Yes, sir. Yes, sir.
Kindly. So here some important data we have prepared. The size of the storage device. If you go, the largest storage device is possible only in a pump mode head. Now the discharge time depends upon the tail rate's storage capacity. Life cycle is very large. Energy density is good and efficiency is good. And still no work is done on this area. Say people always say the efficiency of pump mode hydro station is less. But how much investment has been done? How much geological work has been done? Sir, we have a premier institute like IIT Roorkee who are master in geological science. Did we entrusted them these 5 power plant hydro station? You please take a budget from PhD committee 20 and study properly that whether I can convert this 2000 megawatt to the pump mode or not, and how can I improve the efficiency of the running pump mode hydro station. We are more concentrating on the improving the efficiency of the battery, efficiency of the charging discharging cycle, which is a nutshell. It's a good thing. I don't say you don't do it. But the quantum of balance requirement, quantum storage requirement, probably battery will be far, far behind the capacity can be offered by the pump mode hydro. And it's possible also to convert the existing hydro station into the pump mode, or even side canal of the left canal, right canal of the hydro station into the pump mode with a investment. But it will give a long 60 years is the maximum life cycle. That is nowhere feasible. Other life cycle is less than 5 years, 10 years, something like that. Sometimes it is in hours only. So I want to stress upon that pump mode is having the highest capacity feasible. If we say compressor, modern salt, lithium ion battery, lead acid battery, flow battery, hydrogen, flywheel, it comes to at a very low level. I don't say we should stop research and working upon this other device also. That will be useful and that will play the role at that particular place and particular location. But as far as grid requirement is concerned, and if we are planning 450 GW by 2030 or 175 GW is our commitment for 2022. And the recent meet is much beyond this. And the real carbon neutral we can go only with help of the very good, reliable, long-term storage solution that is a pump mode. Next slide, please. I request for the next slide. Yes. So this is certain setup has been done so far. Kadamparai, Srisalem, Purulia are good operating pump mode plant. I have been told that West Bengal is also going for one more pump mode plant. Other states also have bid invited bid for the pump mode plant. Unfortunately, the Sardar Sir, my host state from where I come, this 1200 megawatt pump mode is not operating. Here it is written partially functioning as per the record, but as I understand, as a grid operator of Gujarat SLDC, it is not operating. Even Kadana, Gujarat state plant is also not operating. So our forefathers were very much visionary. Before renewable, they have thought of pump mode requirement. When these plants were constructed, renewable was zero. Though our forefathers, our precedents were so visionary that they had gone for it. Unfortunately, having felt bad need of this thing, we are unable to restore it back to its operational things. It was planned, it was built, it was constructed, tested, found okay, but not put to use due to various reasons, and our administrative people or supportive people are not able to resolve this. We are talking and arranging seminar for 10 megawatt battery, but we are silent about 1200 megawatt Sardar Saurabh pump mode operation. This is what the sorriest part or pitiable situation in the country due to various reasons. Other are the kindly keep highest. Other proposed are very big scale things. Turga in the West Bengal is being planned. Udam in Tamil Nadu is also planned. Indravati in the Odisha also. 600 megawatt we are planning at Odisha. Sheravati in Karnataka close to 2000 megawatt is being planned. So next slide please. This is some more detail about the Purulia pump storage plant. It's a very good operative plant and live example of pump storage, and West Bengal Discom has been benefited due to this very big way, and it has resulted into a flattening of the load curve, flattening of the availability, and even in surplus time, they are able to avail the market benefit out of the storage energy. It's not only that you meet your peak requirements, sir. It's not only that you pump during your off-peak requirement. Say your power may not be surplus to pump it, but if the market rate is competitive, kindly pump it and use that as a motor and store that energy. When the rate of exchange is at 2 rupees or less than that, and you can sell it at the 8 rupees during the peak hours, 6 rupees at the peak hours. And at that time, the difference of the rate, two rates between the peak and off-peak or the lean period of the exchange, I think even with the 70%, 80% efficiency of the pump mode, it is viable, doable, and it leads to a very good balancing to the grid operator. Next point, please. This can be read and people will share this to all. And this is Turga pump mode project. This is proposed in the West Bengal. It is 215/4. So some details are given and they are taken at a fast trail. So they will do it next. The advantage for the pump mode is it's now coming with a very most mature, reliable technology. The capacity is large. Here we have to stress upon. The state need a balancing in terms of hundreds of megawatt, not a 5 to 10 megawatt. It is a large, large capacity, the long service lifetime, low unit cost, and stabilized grid frequency. It peak shaving means it addresses all the requirement of storage and balancing. There are some limitations also that it needs a geographical condition, interstate disputes on sharing of water, longer construction period, and huge investment. But if we keep the construction cost of the hydro project aside, only think of delta component of providing the pump mode only. Probably the cost of turbine is not making much difference. What is important is you need to have a small dam at the tail rest to store the water which is going out and bring it back instead of allowing it to run away to the sea. So that cost has to be accounted for. Now, if you take up the battery, it also allows the better use of RE, added protection, less depends on the grid. It reduces the carbon footprint, but it has some limitation. Higher upfront cost, more complexity in estimate to get backup load, more parts need yearly inspection and maintenance, and time of the use rate plan and electricity bill if solar system is not sized properly. And I have been told, sir, Pondicherry is the first area which was under the smart grid, smart city, and the power grid has gone for that. 2 battery set has been provided. One is out since more than 1.5 years. Another one is running only when the visitors are there. It has very low efficiency as on today. So 5 years is, I don't think more than 5 years, good operative life cycle of the battery, and disposal of battery also to be think of very proper. Third one is hydrogen storage. That is abundant availability source, water, zero carbon footprint, and limitation that access electric power to produce hydrogen, high cost of setup and maintenance of electrolysis, safety to handle. Safety is very important thing over there. Next slide, please. Generally, the limitation of energy storage is high cost of infrastructure, energy density, complex maintenance, lack of market mechanism, immature technology, unclear application value, inadequate regulatory policy. Sir, this is very important. For any storage device, a proper regulatory support to make it viable and operator. Anil has rightly said, if we see the solar which was bidded at 16 rupees before 10 years, now it has come to 2 rupees. But unless we did not attempt it for 16 rupees, today also we would be far away. So we have to take a call about promoting such thing with a viability gap fund support. Next slide, please.
That's all, sir.
Yes. Now, I would like to conclude like this. This energy storage is a need of time. And I think we all at appropriately have to take a call, and we have to ensure that the state, DISCOM, and the area under which we are authorized or we are supposed to a policy or decision maker or our whatever decision maker, to brief them with the right spirit, right technology, so that we have already missed the bus, but at least we run away and catch the bus. Because if you think of 175 GW up and operative by next year without storage, I think it is an impossible task. It will lead to a lot of other grid challenge. Or what will happen, sir, that whatever has been harnessed in terms of renewable will not be utilized electrically. The plant will be kept out. There will be litigation. There will be dispute. So a storage technology, to best of my knowledge, in India is good, and opportunity to make it feasible. And we all have to join hand together with a proper classification and application. We have to tap the right type of storage for right application. And I think days are good. Government, we have to brief the government, management, and the authorities to go ahead, and whatever viability gap funds are required, that MNRE or MOP need to address upon it. Thank you very much. Thank you for giving the opportunity. I seek some question if any is there.
This pumped hydro is generally used for peak demand only, sir. You are asking to use construct on pumped hydro for exclusively for charging the batteries. But any batteries is inevitable, sir. With the battery only we can move the EV vehicle. Without battery, how it is possible to do the procedure?
No, I don't say like that. Sir, one thing is very clear. Say, to charge a battery also, you are converting renewable power to the AC and you charge the battery. So I don't say we don't stop charging the battery. For electrical vehicle, this as on today or even for next decade, I don't think any other mechanism is viable and suitable. As far as storage requirement of EV is there, battery is the only solution to best of my knowledge. It has been evaluated at various level, various platform, and that is no other alternative to that. Input to that battery, how it will be charged. So we have planned ample renewable for that. So that is feasible. But I think the earlier speaker shared something that isolated renewable project to operate the charging station, we have to take a feasibility call for that as far as technical requirement is concerned. So I have 100 megawatt wind farm. I cannot put up the charging station for the outlets of that wind farm at one location and I will continue charging it, because my charging requirement time and my generation may not match. So the ultimate and optimum way is to dump the renewable power into the grid and tap it wherever you have a charging location are there and use the grid as an infinite bus. Isolated, he referred some Denmark experience. It may be put over there, but probably in India, still days are very far. Sir.
Thank you.
Thank you, sir. Any questions from the participants, sir? And I will check YouTube also. Dr. A. Pandian, sir. Any questions, sir?
Anyway, sir, if no question are there, I can be addressed by email also later.
Okay, sir. Thank you, sir. Thank you for sparing your time, sir.
So
whatever information and a lot of pump details also you have to sharing that, sir. And Tehra and already in Tamil Nadu is also one more project is started at 4 into 250 megawatt Kunda 7 pumped storage scheme, and one more scheme is at Kunda, another 8 scheme is also started, sir. Actually, 2000 megawatt capacity.
It will bring a good result, sir.
Yes, sir. Yes, sir. Because this only very much benefit to our support to the grid system. Because right now we are mostly we are going to contribute our RE power only. So that's concentrated. So that's it will be very much helpful, I think, the pumped storage systems. Thank you, sir. Thank you for your time spent with us, sir. Thank you, sir. Sir, the Genesri, next I want to welcome Mr. Dr. Mindwell Nathan Vehanathan, sir.
Yes, sir.
Just now share with you the thing that you have to share it. Please.
I'd like to invite Dr. Nathan Vehanathan, sir, who completed his BE Mechanical Engineering in MK University, Madurai, ME Thermal Engineering in Anna University, Chennai, and PhD in Thermal Energy Storage, Anna University. He has 20 years of experience in renewable energy industry and in the area of research, planning, designing, development, implementation, and operation of solar power generation and green energy projects in various parts of India. He is an energy engineer with high experience of high energy project management. He is working under the Asian Development Bank fully funded project named Disease Resilient, Energy Efficient, and IoT based centralized air conditioning systems for Tamil Nadu Disaster Management Authority. He has also published several papers related to green energy research. He worked as a project manager in energy audit, residual life assessment in boiler and turbines in coal-fired thermal power plant Tuticorin. He accomplished a renewable energy and energy management consultant with diverse experiences in design, business development, and project consulting. With this brief intro, I would like to invite Dr. Nathan Vehanathan, sir, to light on the topic of battery energy storage system. Welcome you, sir.
Good morning, sir. Welcome you, sir.
Welcome, sir. Sorry, sir. I want to share my screen, sir.
Yes, sir.
I want to share my screen, please.
I don't have that PowerPoint, sir. You share PowerPoint,
yes, sir. I have a PowerPoint, sir. I'm not sending, sir. Now you share, sir. It's
okay.
visible, sir. It's visible,
yes.
Sir.
No, not it. Yes, sir.
Okay. Actually, I would, thanks for this opportunity. You have given me the chance to do some energy storage and all, no? Energy storage or battery and all.
Yes,
but
sir.
I have a slides related to electric vehicle.
Okay, sir. Okay, sir.
Yes, sir.
Go ahead, sir.
Yes, sir. Normally, electric vehicles are experiencing
So,
it's visible, sir.
Okay. Visible, sir. Visible, sir.
Okay. I closed my video because of some network problem.
Okay.
The electric vehicles are experiencing a rise in popularity over past few years as the technology has matured. Okay, normally the cost of the electric vehicles now reduced. Okay, declined, and the support of clean transportation has normally that we are promoting that green energy awareness. No, so we are based on that we are reducing the cost of electric vehicles nowadays reduced. Okay, that's why we are choosing this topic. What are the very low, I think so. Networking is very low.
Yes, sir, you will be visible, sir, your screen.
But myself. Wait a minute. Screen is visible, sir?
No, sir. So please send your PowerPoint. I will share with you, sir.
No, not visible.
Not visible. Okay. I will share. it. In WhatsApp itself, I will share it, sir.
Okay, sir.
मित्र सर उधर बारिश हो रहा है क्या सर? इधर बहुत बारिश हो रहा है सर चेन्नई में.
No, sir. Last week it rained for 1 or 2 days, but now it is not raining, sir. In fact, this year it rained less. Our reservoir level is down, except Viratpur Burla plant. So we'll have a bad time in the summer, sir.
26, 27, 28 3 दिनों में बहुत बारिश है सर. पूरा बारिश में हम लोग ये इंटर कॉन्फ्रेंस कर रहे हैं.
Yeah, but it is good. I thought it will be cancelled, but it is good that you maintain the tempo and you manage it, and it is a good seminar, sir.
Thank you, sir. Thank you.
I'm told that Tirupati is cut off totally from the other area.
Yes, all roads are cut off, sir. No communication is there. Problem in Andhra also they are affected a lot.
Yeah, yes.
Generally in Odisha only the problem will come. This time it has changed.
Now it is diverted slide down to the Tamil Nadu.
Yes, sir.
Sir, I sent, sir. Sanil, sir.
Yes, sir. Please, sir.
I sent. You share my screen.
Just a second. Okay, sir. I will down. So is it visible, sir? Okay, sir.
Yes, sir. Yes, sir. Yes. Next slide, sir. Next slide. Next slide, sir.
Thank you. Okay, sir.
Okay, sorry for the delay. It's an overview.
problem, sir.
Actually, my overview is an overview of a status of light duty EV market.
Yes, sir.
Then current projection of future adoption. The insights on market opportunity beyond light duty EVs. Then review of cost and performance evaluation of batteries, power electronics, and electric machines that are key components of EV success. Then charging infrastructure status with a focus on modeling and studies that are used to project charging infrastructure requirements and other economic public charging. An overview of impact EV charging on power system at multiple scales, ranging from normally bulk power system to distribution networks. Then insights into life cycle cost and emission studies focusing on electrical vehicles, and future expectation and the synergies between electric vehicles and other emerging trends and technologies. These are the overview of my presentation. Next, sir. It may my presentation actually is summarized into nearly 7 or 6 parts under. Okay, first one is an EV adoption, electric vehicle adoption. Normally, the light vehicle duty. Normally, the EV nowadays more of the EVs are invention are by light duty only because of the needs after 2010. Okay, in the mid of 2010, the needs of electric vehicle increased. Okay, so because of the 3 pillars and normally 3 important factors that define that EV adoption standard. Okay, the improvements in battery technologies. First one is the improvement in battery technologies. Then a wide range of supportive policies to reduce emissions. Second point. Then third one is an promote energy efficiency and reduce the petroleum consumption. Okay, these are the 3 important points for electrical vehicle adoption. Okay. Then next one is in batteries and the EV other technologies. Okay, nowadays the technologies are related to the batteries very much improved. Okay, and over nearly last 10 years, the price of lithium ion batteries packs has nearly dropped more than 80%, from $1,000 kilowatt hour to 156 kilowatt hour. Okay, so the last 10 years, the lithium ion batteries cost very well reduced. So then the specific energy of lithium lithium ion batteries also increased. Okay, the specific energy increased, then the cost is reduced. Okay, that's why they all are choosing that electric vehicle. Okay, it's a reason, main reason. Then charging infrastructure, I will explain later. But the small, normally the few million light vehicle EVs on the road currently. Okay, there is about in US itself nearly one public charge point per 10 battery electric vehicles. Normally in US itself, 10 for a single vehicle, electric vehicle, they are having that. 10 electric vehicle, they are having one charging point. So we have to improve the charging point. After that only we can enhance their activities of electrical vehicle. Okay. Then power system integration. Next point is in power system integration. Then this one is an accommodation of EV charging at the bulk power system level. Okay. Then in different each region, it's like a power system, like it may be a grid or it may be a renewable source. Okay. Then life cycle cost and emission. This is also one of the important factors to consider for because of the life cycle cost. Normally, the many factors contribute to variability of EV vehicle life cycle emissions. Mostly the carbon intensity of electricity, charging patterns, then vehicle characteristics, then even normally in the load climate. These are the important factor to design that life cycle cost of the equipment. Okay. Then greenhouse emissions. Another one part is in greenhouse emissions. And normally there's electric vehicle is having zero emission and all. Okay. So there is a main important point to consider the design of before going to consider the design of EV what and all. Then synergies with other technologies and the physical expectation. Normally we are nowadays the hybrid vehicles are coming. The hybrid vehicles are operated by hydrogen with electric utilities. So these are the some hybrid options we can make it because of for using EV adoption. Next slide. Okay, in the worldwide market by vehicle in future. Okay, then electric vehicle normally the 2000 blue in color is in 2020, the red in color is in 2030. Normally the electric vehicle, then a hybrid, then diesel, then gasoline, then fuel cell. Okay, so the market occupancy we are expecting that in 2030 itself, nearly 30% of electric vehicle become. Okay, so the gasoline will also decrease. Then diesel somewhat increase in diesel, then fuel cell and okay. So these are the some the worldwide market occupancy in vehicle in future. Next. Next, sir. Okay. This is an US itself, a Department of Energy, United States of America. They are it is in vehicles, various vehicles under the EV. Okay, EV category. Then it is in Transpower, then Orange LV, the Tesla, then Bluebird, then BYD, then Smith. The BYD is a China company. It is in battery capacity in kilowatt itself. Okay, so then weight class is increased. Weight 8 mean that up to 6 to 8 weight class it increased from these are the trucks and all. Okay, the trucks and all using this type of applications. Then next. Okay, there's a batteries, power electronics, and electric machines. First, we consider that lithium-ion battery price outlook. Okay. So lithium-ion battery nowadays, most of the electric vehicles are using lithium-ion batteries only. Based upon the price reduction, most of the vehicles are using lithium-ion only. Okay. In 2010, it's cost about $1,200 dollars per kilowatt hour, but it gets reduced up to 2020. It's around 200, around 156 like that. Okay. So in 2030 itself, the price will reduce up to $62 per kilowatt hour. Okay, we are expecting that. Next. Then integrated electric vehicle system and the inverter power density for several commercial light-duty vehicles is an DOE, the Department of Energy, shows that. So the various companies, the BMW or Prius or Leaf. So target 25 is a 30. So density itself. So density based upon that we can they are the target itself. So we can increase the electrical drive system power density. We can increase based upon that inverter power density. Next. Okay. Next, charging infrastructure in 2019. Okay, it's a public charger by base electric vehicles. Normally the 0.0 to 1. Okay, so it's an integer or indicator. As China having the highest public charger, and then USA, then Japan, then UK, then Netherlands. We are not in that line. Okay, next. Okay, there's a charging, smart charging. Okay, advanced forms of smart charging. Then V1G is a unidirectional controlled charging. The vehicles are charging infrastructure normally adjust the rating of charging. It is like a commercially vehicle charging, like a petrol bulk, like that. So the V2H is in the vehicle to home or building. We can charge the vehicle in a power supply to the home itself. Okay, so home itself we can charge that. Then a grid, vehicle to grid, directly vehicle to grid. Then a smart grid controls the vehicle charging and return electricity to the grid. These are the advanced form of smart charging. Next. Next. Okay. Here, smart charging enables EV electric vehicle to provide flexibility. How it's flexible? Okay. The current concept of smart charging includes, namely, the time of use, pricing without automated control. Okay. The time of use, normally the pricing without automated control. Then a basic controlled, it may be on or off. Then unidirectional control. Then bidirectional controls. Then dynamic pricing with the automated control. These are the basic concept. Okay. So current concept used in smart charging system. Then smart charging enables EVs to provide grid services. Through grid services, we can basic smart charging like that. Then flexibility provided by the electrical vehicles. So the advanced charging like that, low to high. So it having some flexibility. Then next, sir. Then they same flexibility. The potential range of flexibility services by electrical vehicle. Then system flexibility, then local flexibility. The system itself, the wholesale market at a peak saving, then a portfolio balancing. These are the some advantages. Then a transmission system operator, the frequency control, then other ancillary services. These are the some examples of a transmission system operator. Then local flexibility, the distribution system operator, then voltage control, local the congestion and the capacity management. So the distribution system operator, we can manage the capacity. Based upon the capacity, we can manage the behind the meter, it's increasing the rate of renewable energy self-consumption. It's a green energy. Okay, then arbitrage between the locally produced electricity and the electricity from the grid. So these are the behind the meter is a then backup power. So backup power, it's like a storage like that. Then next. So then short-term impact of EV charging. Normally in the EV charging, the short-term, long-term is there. So EV charging selected by that solar power or VG1 or V2G. Already I explained that V2G and V1G. So the V1G and the V2G mentioned it. So the curtailment the business normally up to that business as usual, the curtailment is 0.5. Then VG1, the charge peak load and the charge average short run module cost, then change in CO2 emissions and that. So based on that value will vary. Next we'll go for a long term. Okay, long term impact of EV charging. So EV charging itself, curtailment and change in yearly peak load and okay. So the wind based system, another one is in solar based system. So wind based system having that more higher curtailment, I think so. So here the lower solar based system having that lesser curtailment only. Then a change in peak load also for less in so wind based system. Here also some small variation is there between the wind and the solar system. These are the long term impact EV charging with the green energy. Okay, next. Okay, the impact of EV charging on electricity grid. Normally studied by the IRENA, then scenario, the 50% penetration is isolated system by 27% solar say. Our ultimate aim is to provide the charging by solar or wind and or anything hydrogen based energy. So the 50% penetration in isolated system with 27 solar share, but uncontrolled charging means it's increasing peak load 0.5%. So various agencies are giving various scenarios and uncontrolled charging and smart charging. So the uncontrolled charging will reduce that performance of the system. The smart charging giving a effective utilization of the power through EV charging. Next. Okay, then vehicle grid integration is an important part. Normally, the smart electric vehicle grid integration can provide flexibility. Already I told that the ability of power system to respond to change in demand and supply by charging and discharging vehicle batteries to support grid planning and operation over multiple time scales. So this is very important. The life cycle is very, very important. So flexible also important. So the smart electric vehicle grid integration can give flexibility and more life cycle system also. Then here having that the generation capacity and the transmission distribution plan. So in the power system application, then a time scale, then vehicle grid integration values. The ability to reduce peak load and the capacity requirement. Then resilience to extreme events. So in graph itself, you can show you can see like capacity requirements and that. So in the power supply like that. So then demand is in total line. The demand is in the demand response is in the green point. Then intelligent demand like that. Okay. So interactive demand. Then resilience to then the seasonal planning. Hydro long-term storage dispatch. Told us hydro pump storage and all. No? So seasonal planning and all. So long-term storage dispatch, it may be in monthly, we can store. Then commitment and dispatch decisions, it in days to hour storage only. The leverage EV storage and all, no? Leverage of EV storage. Then balancing and power quality. Then seconds to sub-seconds. Then support in consumers. This is a yearly, you can store it. Okay. So time scale, later to the time scale, it is in this one, a generation capacity and transmission planning and all. No? So this having highest year of storage. Okay, next. Okay, life cycle cost of emission. Then EV vehicle. Okay, so these are some market potential, generation, then grid, the temperature overall. This on that. Okay, life cycle cost. Next. Next one. Okay. Okay. This one, our part thermal battery thermal management system. Normally, the main drawback of using electrical vehicle is to heat generation by the batteries. Okay, the battery thermal management system is used to maintain the temperature at normal level in order to avoid breakage of burning of the batteries. So the battery management system is a battery thermal management system is very, very essential to control the temperature. Then this function is to monitor, control, and manage heat dissipation. Then optimize the performance. Then vehicle categories like high duty electric vehicles, then power electric vehicles, plug battery vehicles, then battery types, lithium-ion batteries, nickel cadmium batteries, then nickel metal hydride batteries, lithium-ion polymer batteries we are using up to 0 to 200 kilowatt hour. Then second range is medium range is 200 to 500 kilowatt hour. Then 500 is greater than 500 kilowatt hour. Then management system types, it's like active system, and then forced or liquid flow system, and then thermoelectric cooler. So I will explain later. Then passive system, natural air cooling, like two-wheeler engine and all. No? So natural air cooling. Then using phase change material to control that. Then heat pipe used to manage the temperature rise. Then features like easy to install, then small in size, then load less weight, then inexpensive, easy to operate, the reliable, no harmful cases. These are the importance of battery thermal management system. So next, okay, this is a lithium-ion battery structure. So anode, then cathode. So discharging lithium, then discharging, charging lithium, and discharging lithium and all. So separator. So ions and all, no, charging electrons and discharging electrons. Okay, next. Okay, the heat generation or heat loss distribution in a battery cell. The heat loss distribution, it be a reversible heat or reversible heat. It's a reversible heat. It is due to the intercalation or lithium and intercalation of lithium ion at a cathode, then intercalation of lithium ion at a anode. So lithium ion cathode and anode already I explained in the previous graph itself. So then a reversible heat is a ohmic heat loss, then resistance of solid electrolyte say, then resistance due to charge transfer electron interface, then resistance due to diffusion. These are some causes of heat loss distribution. Then next. Okay, the result of heat generation in lithium ion cell. So in the lithium ion cell is some carbon anode, then cathode. So due to that temperature increases, that chance to burn off batteries and all. No? So heat generation like this. Okay. So next. Okay, this is a thermal runaway characteristic of lithium-ion battery. So the arc it is a measuring material, measuring equipment. Through this, we are before runaway, then after thermal runaway. The inside the chamber itself, we can find out that how the thermal, the heat, it's affect the performance of the lithium-ion batteries, how it damage the batteries. So it is a setup for the thermal runaway. Then next. Okay, then there is some system for cooling. Okay, the boiling fluid system nowadays in our EV electrical vehicle itself, in front of that heat exchanger is there, radiator is there, then fan. So the cells are laying like this. Okay, then porous material, thermal sensor and all. So it passes the cold water through the circulation. You can get that. You can reduce the heat. Okay, so these are one of the battery thermal management system. Then next. Okay, how it arrange the battery packs? So it's aligned battery pack, then staggered battery pack and a cross battery pack. Between that, we are adding some material to reduce the heat generated by the battery. Next. Okay, it's a liquid cooled. Already I explained that liquid cooled battery thermal management system. It's a battery module. So cooling channel, already cooling channel, cooling plate is there. Then battery cells are there. Then cooling plates are there. Then cooling channels are there. So single group. Okay, this is a single group. We can transfer the heat like that. Next. Okay, the liquid cooling system and all. Okay, like a IC engine powered vehicle and automobiles and like electric vehicle also we can have some system. There's a radiator system. Through the radiator system we can pass the cooled water. Okay, cooled water through the battery, lithium-ion battery package. We can reduce the heat. Next. Okay, it's a thermoelectric cooling model. Already I told that thermoelectric cooling model. It's an external electric connection. Using electric connection, you can give the you can control the heat through this one. Okay, next. Then electric vehicle thermal management system. Normally, in normal vehicle, we are using air conditioning system through the air conditioning system. The compressor is connected to the IC engines. Okay, that internal combustion engine flywheel and all. Okay, they will rotate. The compressor also rotate. Okay, so but here itself there is no IC engine part at all. Okay, but here we are using air conditioning system using some battery system only. Okay, so the electric power thermal control system, then HVAC system, then thermal storage heat recovery system, so liquid cycling system on that. Next. Okay, this is the using some phase change material. Okay, phase change material means normally the wax is a phase change material. Normally water is a phase change material. Why it is called as a phase change material means Phase change material means it will change the phase. You increase the heat, it will change the phase. For example, if you take ice, okay, ice is in solid state. Okay, if you give the heat to the ice, automatically it converted into water. Okay, what's the meaning for it? If you are supplying the heat to the ice in particular temperature, like 0 degrees Celsius, it converted into water. It is in boiling point of ice. Okay, then further heating water. If you heat the further heating of water, the water is converted into vapor. Okay, for a particular temperature, 100 degrees Celsius, it is a boiling point of saturation point of boiling point or saturation point of water. That point, the temperature is constant. That is an isothermal process. Okay, if you continuously supply the heat, the temperature is constant. The phase will change from water to the vapor. Okay, so this is a basic concept of phase change material. This phase change material can be used to control the temperature in that battery systems. So the battery thermal system can be classified into internal and external thermal systems. So these are some classifications under. Okay, so mostly the PCMs are used as a phase change material. In my research, I'm doing various phase change materials to reduce that battery thermal for Minda is a Pune, is a company in Pune. I'm doing a research for them. They are making a electric batteries for electric vehicles. Next. Then battery for a phase methodology approach, design model. Normally, design specification, cell selection, electrical scheme model. So array of cells, then BCM selection, then modeler like that. So right side itself, cells, casing, and heat exchangers. So okay, next. Okay, these are some assemblies. I make some assemblies. It's a PCM air cooling system. So batteries are inbuilt in that. Normally the casing under. First the batteries with thermocouple, then a skeleton of model, then the batteries inserted into the hole, then slides, then sealed, then electric connections completed. So in right side itself, already I told that PCM and the PCM air cooling, then PCM liquid cooling. So batteries, BCM. So these are the system. Next. Okay, this is an EV integrated thermal management system. HVAC already I explained. The first one is an integrated EV system. First, the ambient air passes over the condenser evaporator. Okay, then cooling radiator is there. Okay, like a ordinary vehicle, our automobile center. But the engine is not there. Not there. So before that, between the last, the PCM thermal storage is there. Then thermal pack thermal circuits are, sorry, battery pack thermal circuits are behind that. Okay, then electric motor. Okay. So this is the structure of the integrated EV thermal management system. Then National Renewable Energy Laboratory, United States of America, they are having electric vehicle thermal management system. Okay, then ambient air passes through the condenser. The condenser is passed through the circle is there, cycle is there, refrigerant cycle is there, refrigerator compressor, expansion valve, then evaporator. So pass the ambient air is passed through this. So this is second one, middle one is an electric vehicle thermal management system. Then cooling and heating loop. So the final one is the heating and cooling loop. So this is a structure of EV integrated thermal management system with the HVAC. Next. Thanks. Thank you for your taking. Thank you. Any questions on that? Anil sir, thank you, sir.
Yes, sir. Yes, sir. Yes, sir. 1 minute. Dear participants, any questions? Correct, madam.
Sir, good afternoon, sir. This is Pandian.
Yes, sir. Please.
So, Mailandran, sir.
Yes, sir.
It's a really wonderful work you have done in the area of CV. So I have one question on PMS system, sir.
Okay.
Actually, you know very well, if there is any one cell gets problem, there is a thermal overloading issues are there.
Yeah.
So how can we do, sir? Now IoT device, many latest technologies are using.
Yeah.
Is there any possibility, sir? How
Yes, sir. Yes, sir. We can find out, sir. We can find out based on the thermal characteristics. We can identify the problem. Okay. If only thing how it damage me, automatically can temperature will increase or decrease. Based on that, we can put every systems, every batteries are connected with IoT. Not only based on thermocouple. I already explained in one slide itself. In package itself, every batteries are connected with one thermocouple. Okay. So if you one backup increases, automatically it fix the problem. Automatically fix the problem.
Actually, one of our professor in KL University Mechanical Engineering is doing a thermal image capturing method. They are identifying the battery stress and everything.
Okay. Where, sir? Where, sir?
In KL University, sir, Andhra Pradesh.
KL, yeah, okay.
Dr. Murali is doing that work. Battery management system with thermal imaging. By taking image.
Great.
Continuously, they are going to take some time of gap. With that image, they are identifying by using AI techniques and machine learning.
Okay.
They are going to find out the cell issues and that.
Okay, sir. But the research point of view is okay, sir. But
real time,
it's difficult. That's why we are using the thermocouples. Thermocouples are integrated with this. Okay. So using thermocouples, you can identify the problem. So then using that IoT devices, AI and all, we can fix the problem in there itself. Okay, that is the research that I am doing, sir.
Okay. Yeah, whatever technology you are using, same technology in Vijayawada, there is one company called Effectronics. They are doing LED manufacturing as well as battery, and they are doing a lot of work, content work in railways. Railway battery management system through IoT, they are controlling them. Whatever you can know by using that concept. Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.
And then is there any questions from our participant side, sir? And I will check that YouTube. If any other questions, please ask me. So, and then from your PowerPoint side, sir, potential range of flexibilities services by EVs, system flexibility and the local flexibility. You have to mention that, sir. The voltage control and local congestion and the capacity management managed by the only distribution operator. Only have to mention. That is more difficult on that present situation after implementing all this.
Sorry.
Local flexibility, sir.
Yeah, local flexibility. Okay. Distribution system operator. Okay.
Yes, sir. Yes, sir.
Yes, sir. So voltage control.
Yes,
what?
Sir.
Which one, sir? Distribution system operator.
Yes, sir.
What's your question, sir? What
How it is difficult to control that right now management is difficult in the distribution side. It is a large distributed network actually.
Yeah. Yes, sir.
That's why it is difficult to manage for implementation of the electric vehicle. So that's why what are the new technologies implemented in the other states?
Yeah. Yes, sir. IoT based normally that all the systems are integrated with connected with flexible systems. Now one centralized systems on that can be controlled by IoT based systems. Advanced.
So microgrid system you have to implement and you have to manage that system is only possible. Otherwise it is difficult.
Yes, sir.
Okay, sir. Right, sir. Thank you, sir. And then any questions, sir? Balaguru or anyone have any questions? So thank you, sir. Thank you for your valuable input in that energy manager EV electrical vehicle, the thermal energy storage systems. Because your expertise in the mechanical engineering side, and you have to do a lot of innovative projects and patent all related with that electrical vehicles only and thermal related materials. I think.
Yes, sir.
And I experienced in that lot of works. I have just now noticed all those things. Your lot of projects also you completed.
Yes, sir. Yes, sir.
With a UTOS and solar expert and noticed, sir. Thank you. And then you have a thermal auditor also in that experience in the 700 megawatt per solar power plant auditor as per IEC 62446 standard. That is what's
Yes,
that? That is IEC.
Yes, sir. It's a standard for auditing, madam. For a solar PV system.
Okay. Right, sir. Right, sir. Thank you, sir. Thank you for giving your valuable time to spare with us and sharing your knowledge and things.
Thank you very much, sir.
Thank you, sir. Thank you.
Okay. Thank you.
Very good afternoon to everyone. Today's morning session is over, and the next session is started at exactly at 14 hours. And today's fourth session is completely successfully going well. And then next session started at 14 hours for conclave session and then debate, and finally it goes to valedictory function. Thank you.
Thank you.
Please join at 14 hours, 50 hours, and we'll start at the 14 hours conclave meeting. Okay. Thank you. Thanks everyone. BB Mehta sir, thank you sir. Very thank you sir. My William sir, thank you sir. Madan Kumar, get ready for that debate event. Balamurugan. Sir, 1 minute, please. I will stop.